Good morning, everyone. Great to see you back. I don't see too many of you yet, so I suspect there will be lots more coming. So it would be great if you could move a little bit more to the inside for all the late people, especially if you're sitting on the borders. Thank you. I don't see lots of movement yet, but we really appreciate it. Great. So having said that, our first talk this morning will be given by Hal Haggard. He is not only a phenomenal researcher, but also a great instructor. So we asked him for the daunting task to review all of loop quantum gravity and spin foams. And luckily he was up for it. So I'm very excited to learn more from you, Hal. The floor is all yours.
Good morning. Thank you for being here. I want to add my thanks to everyone else, to the organizers. It's been an incredibly tightly run and wonderful conference so far. As Beatrice says, I have three fields to overview. They asked me to do loop quantum gravity, spin foams, and my own research. So I'm going to go at quite a clip. If I'm going too fast, wave your hands and I'll try to slow down a little. So just to give you the barest overview of what I'll be talking about, loop quantum gravity is the Hamiltonian approach to quantum gravity, where we make a space-time split and we consider the theory from that perspective. In particular, it's a gauge-theoretic approach to quantum gravity, and that's going to be where I'll start out, and I think it's a compelling aspect of the theory. On the other hand, spin foam models are a discrete geometry path integral. So it uses the same sort of algebraic structures that underlie loop quantum gravity, but it's a path integral approach and is where we're attacking the dynamics of the theory. So I'll give you the talk in three parts. I will overview loop gravity first, and then I'll do the short interlude where I'll introduce you to some of my own research. And then from there, we'll go on to the discrete geometry path integrals. The three parts are mixed intentionally, and in particular, my introduction to the spin foam approach will be non-standard. So there are excellent reviews of the so-called EPRL spin foam and FK spin foam. You can check out Alejandro Perez's review, but I'm going to give you an introduction to some of the approaches that have been developed in recent years, and in particular try to emphasize what I think they've taught us about spin foams. All right, as I already said, loop quantum gravity is a canonical approach, and so we make a space-time split. But the symplectic structure of the theory in the standard metric variables doesn't cast the connection as one of the canonical variables. And if we'd like to see GR as a gauge theory, it's very nice to have the connection at the fore as one of our variables. So in the ADM formalism, the oldest approach to canonical quantum gravity, you split the space-time metric into a spatial metric and a lapse and shift piece. And in particular, the canonical analysis leads you to consider the extrinsic curvature. So here's our spatial slice sigma. And we think of the extrinsic curvature of as being how this slice is embedded in the space-time. And that leads us to a canonical momentum, which is actually given by essentially that extrinsic curvature. In the approach that we'll be taking, where we try to center the connection at the fore, we're going to shift to a different set of variables. And the first part of that shift is to reorganize which part of the metric we think of and to introduce this densitized triad. So it's just like a tetrad variable that you may have seen in classical GR, but it's a triad, a frame field that lives on the spatial slice, and it's been densitized by the determinant of the spatial metric. You can recover the metric, of course, from the triad. And in particular, the variable that we'll be focusing on a lot, because it's a very useful way of framing this triad, is in terms of a 2 form. So we call this the electric flux 2 form. Then we need the connection variable that's going to be the other half of the canonical pair that we think about. And to do this, you take the spin connection. So we're thinking of a Lorentz bundle that's living over the same space-time. We take the spin connection of that Lorentz bundle and we break it into its boost and rotational parts. And from the rotational part, we can build a connection variable that has the same index structure. Just using the Lorentz bundle's internal Levi-Civita symbol, we can take this spin connection spatial piece and turn it into a connection. In particular, if we require that our triad variable is metric compatible and torsionless, then the same sort of thing that you're used to from tetrad variables comes through, and you can cast this connection as being a function of the triad. All right, so this choice of variables is what makes loop quantum gravity into a gauge theory. In particular, if we take, again, another contraction of the extrinsic curvature with our triad variable, we can build this index structure for the extrinsic curvature. And we take our ADM kinetic term, and you can see how it is re-expressed in terms of these curvature and triad variables. And in particular, you can pick out the kinetic piece in that variable. And what we see is that the densitized triad and the extrinsic curvature are the canonically conjugate pair. So this is our PQ dot in the formulation that we're headed for. So this allows us to set up schematically this Poisson structure. We had that Q and pi were conjugate, and by this change, this canonical change of variables, we have arrived at K and E being canonically conjugate. Unfortunately, K is still not a connection, but we take advantage of something that you know well from your GR courses, that the difference of 2 connections is always a tensor. So we can add any tensorial structure to our connection, and it's still a connection. So this is where the Ashtekar connection comes from. You take the spatial part of the spin connection that we already were discussing, and you add I times the extrinsic curvature. And this is your basic connection variable in this approach to gravity. This is a beautiful idea. It mixes the 2 pieces, you see. The canonical conjugacy is going to come from the K piece, while the fact that it's a gauge connection is coming from this spin connection that we were taking advantage of. So this is what gives the Ashtekar variables this canonical structure in this approach to GR. This is a beautiful gauge theory in my mind. This is the foundation, the root of loop gravity, and what I think is one of its most stunning structures is that the action becomes a completely constrained system. So we have the kinetic term that we just described, and we have 3 Lagrange multipliers that impose 3 constraints. These are the completely constrained part of the theory. Those 3 constraints are the Gauss constraint. This is the gauge theoretic piece that you would be used to. This is the SU2 gauge part. We have a spatial diffeo piece, the vectorial constraint, which is built out of the field curvature of the connection we've introduced. And it's just the contraction of that. And we have the scalar constraint, which is, again, a polynomial in the E's, quadratic at most quadratic in the E's and quadratic in the A's. So this is not only reformulated GR as a gauge theory, but it's also cast it as completely polynomial constraints, and the action has become polynomial. So this is a beautiful approach to GR. It's completely equivalent to GR as a classical theory. You know there's a catch coming because it's quantum gravity. And so the catch is that this I that you couldn't have missed in the definition of the Ashtekar variables. So in terms of I, a slightly further analysis than I've given you here shows that the boost part of the spin connection is actually related to the extrinsic curvature. You can do this by analyzing what's called the Holst action. And there's this nice structure that we're taking advantage of, that the Lorentz algebra, SL2C, can be split into SU2C plus SU2C. These are the self-dual and anti-self-dual sectors of the theory. So this choice of variables that we've just made is taking advantage of that, and we're nicely introducing a connection that is encoding in its real part the parallel transport of the spatial piece of the field, and in its imaginary part, the parallel transport of the, say, RT plane. So this is a gorgeous way of thinking about this connection. But to make sense of it in a quantum theory, we would need to know how to extract those two pieces, to extract as operators what the real part and imaginary part of this connection are. And so far, that's remained a challenge. Despite being a challenge, there's a beautiful recent paper by Stefan Alexander, Herzog, and Laurent Friedel that one of the things they asked me to do was advertise places where, as students, you might think about looking. And this, they've introduced an inner product that's based on the old work of Bargmann. And it's a complex inner product that allows you to do some of this pulling out of the real and imaginary pieces. It's not a complete story, but it's got a really interesting avenue. And this is one place that, as a young person, you have all these experts in quantum gravity who've tried the reality constraints much of their career. It's your chance to see why that doesn't work, ask them about it, see whether this is an avenue of progress. I think this is a good time to think about this question again. Nonetheless, what people have done instead, since they've struggled with these reality conditions, is to modify this Ashtekar approach and to introduce real connection variables. So it's the same spatial piece of the spin connection we talked about in extrinsic curvature, but instead of putting an I here, we put a gamma. And gamma is a real parameter. It's a new parameter in the theory. It's often called the Barbero-Emirzi parameter because these two researchers introduced this way of thinking about the connection. And I'll mention what its physical import is later in the talk. But for now, I just want to give you a brief overview of a kind of tension between different variables. So we've seen already that the Ashtekar variables give us nice Poisson commuting connection. And they actually behave well. I didn't say this before, but they behave well with the constraint algebra. In particular, that scalar Hamiltonian constraint that we saw, when you see how it acts on this connection, you see that at least on shell, it acts as a diffeomorphism. So this is a beautiful aspect of that Ashtekar connection. Unfortunately, at the quantum level, the reality constraints have been hard to impose. So this Ashtekar-Barbero connection has a different trade-off. With the Ashtekar-Barbero connection, you have a real variable. It's still Poisson commuting, so you retain that advantage of the formalism. But it doesn't have a nice algebra with the Hamiltonian constraint. So I'm calling that algebraic aspect space-time covariance here. It's much harder. You can see why this is happening, right? We're no longer cleanly separating the spatial part of the parallel transport and the boost part of the parallel transport. We're mixing these two things. And I, for one, don't have a good geometrical way of understanding what that mixing is doing. So that's the disadvantage of this real variable. Nonetheless, this is the path that is most taken in loop gravity. Just to finish out this classification of connection variables, there's a nice paper from the early 2000s. Alexandrov worked out a third possibility. He studied the most general connection you could have in this context and showed that you can do the third option. That is, you can have a real variable, it's closely related to these Ashtekar-Barbero variables, that does have a good algebra with the Hamiltonian constraint. Unfortunately, this time it's no longer Poisson commuting. So if you want to try and construct a functional representation of wave functions on the connection, this becomes a difficult path to go down. So we don't know of any path that has all three of these properties at the moment. And as I was encouraging you a moment ago, I'm very curious, and I think one of the most beautiful aspects of loop gravity is this Ashtekar variable. I'm curious if we can push this further with the knowledge that we've gained in recent years. All right, so we've cast general relativity as a gauge theory. We're interested in quantizing it, and so it's natural to look to gauge theories, and lattice gauge theories I'll make a lot of comparisons with, for what kinds of observables we would look to. So in an abelian gauge theory, you have the so-called electric and magnetic fields. They're nice local observables, and you could work with them. In the non-abelian theory, the field strength is no longer gauge invariant. And this isn't a great option for looking for gauge invariant observables. You could also look at a sort of transverse traceless gauge and think about that. This is still possible. In fact, this is related to a lot of the work that's been happening on corner symmetries, BMS algebras, and things like that at infinity. But the final option, the one I'll pursue for now, is that you can look at holonomies around closed loops. This works both in the abelian case, where the gauge transformation is killed by such loops. And as long as you take traces, so-called Wilson loops, of these holonomy observables in the non-abelian case, this is again a good observable. So why aren't these used more in, say, lattice QCD? Well, in lattice QCD they are used, but in continuum approaches to Yang-Mills theory, well, the reason is that these Wilson loops have the difficulty that they distinguish loops that are even slightly different from one another. So another really elegant aspect of loop quantum gravity is to use the huge gauge group that we have in the theory to address this and to make Wilson loops into good observables. So the way that we do this is that we have not just the gauge, the SU2 gauge theory that I was introducing, but we have the huge diffeomorphism symmetry of the manifold. Here we're implementing it as the vectorial constraint and the Hamiltonian constraint. But nonetheless, we can use the spatial piece of that diffeosymmetry to identify these two loops. So in loop quantum gravity, we're leveraging these two things against each other. Usually Wilson loops are our difficult approach, but here, because of the diffeosymmetry, we can recover them as nice observables. In fact, the spin networks that you've heard a lot about already at the conference and that we work with so much provide a basis of inequivalent loops. So even if we have diffeos identifying two loops like this, graphs with vertices, well, they can't be diffeomorphically transformed into each other. This depends a little bit on the technicalities of what kind of diffeosymmetries you're thinking about, but graphs and knots are not equivalent loops. So spin networks provide a basis for these inequivalent loops and give us good things to calculate Wilson observables on. So the idea then of loop gravity, the quantization that we'll be thinking about, is to introduce a Hilbert space based on these group variables, which are the holonomies. So this would be the SU2 group, and using the Haar measure. In particular, we'll consider graph embedded in space-time. On that graph, we will have L links, which I'll label by indices little l, and n nodes labeled by little n. And you can have holonomies along every link. And so just by tensoring this Hilbert space, we get a Hilbert space for the graph. Finally, we need to take the gauge invariance at the nodes of the graph into account. And so we divide at the nodes by SU2. And we have a good Hilbert space for graphs. To define an inner product on this Hilbert space, we leverage another tool from lattice gauge theory, which is a so-called cylindrical consistency. So I'd like to be able to take the inner product of a state on one graph with the inner product of a state on another graph. But to be able to do that, I would need to be able to see both of these as being in the same Hilbert space. And so the idea is to embed smaller graphs in larger graphs where I just color the link that is additional with a 0 representation. Then it doesn't contribute to my inner product, and I can think of both gamma and gamma prime as subgraphs of this larger graph and take the inner product there. So this gives us an inner product. And as we consider the refinement limit of more and more finely worked out larger and larger graphs, we approach a continuum theory. There are important differences with lattice gauge theory, as well as all these analogies that I've been telling you. So in a lattice gauge theory, you would have a lattice spacing, and that lattice spacing would mean something physical. It would be the physical distance between, say, the atoms of your theory. But in this approach, of course, we don't want any background metrical structure. The metrical structure is what we're computing on the links of the graph. And so the refinement limit is actually the limit where we're capturing more and more degrees of freedom. So this is a subtle and delicate aspect of the theory that's much under study. All right. So the summary of this first part of the talk then is that we have a well-defined construction of a kinematical Hilbert space. This is the Hilbert space on graphs that I just described for you, which consists of cylindrical functions. So functionals of the connection variable, which we compute holonomies along the graph of, and we develop a wave function of those holonomies. So the physical content of these wave functions is that they're probing the space-time curvature around closed loops of our graph. Through this discussion, I've abandoned the metrical degrees of freedom. They've become hidden. And so in the next part of the talk, I'll try to overview briefly where they are. I'm going to do this in a very simplified context. But the idea is to go back and look at the Gauss constraint. I left it behind because you know well how to study Gauss constraints and how to solve them. We can think, for example, of integrating the electric two-form that we introduced above. The only thing that's new here is a basis for the SU2 algebra. Integrating it over a closed surface, and of course this gives a notion of an oriented area for this surface. Because the surface is closed, that orientation closes up, and we have 0. So this is a way of thinking about solving this Gauss constraint. Even though this is something you know well and is sort of trivial, there's also a beautiful aspect of this that because the theory is non-abelian, you may not have noticed before. So this is picking out an oriented area, but oriented how? And here the idea is that the orientation is a local orientation. This is much like how the wonderful Jim Hartle, these figures are from Jim Hartle's undergraduate text. Unfortunately, he's just passed away. He gives a beautiful description of how we measure energy of particles, right? We have a local laboratory. We set up a local inertial frame in that laboratory. And what we mean by the energy of the particle is the particle as measured in that orthonormal frame. So the same idea is what's at work here. The orientation of this area element that I was just showing you is that I set up a little region of space-time in my laboratory, and I measure the areas in that space-time region. Of course, if I want to be doing, this laboratory is supposed to be a weak field laboratory. So you're either considering very small regions of space-time or very weak fields, whichever limit you like to think of. So a particularly nice and simple example of this is to imagine that I just have a simple polyhedral region in my local laboratory. And I'm going to measure the area fluxes in that local frame. And the closure constraint just becomes the simple addition of the vectors associated with each of the facets of that polyhedral region. So Gauss closure becomes closure of my geometry here. Here it's just a Euclidean flat geometry. And wonderfully, this is exactly the characterization of polyhedra that Hermann Minkowski gave at the close of the 20th century. So he showed that convex polyhedra are in one-to-one correspondence with vectors that add up to 0, where each vector is equal to, each vector has direction perpendicular to the face of the polyhedron and area equal to the magnitude of this vector. So this is a one-to-one correspondence between polyhedra and their description in a local inertial frame. A very small piece of geometry that is kind of trivial, but that we're going to use briefly. You probably know well that the volume of a tetrahedron can be written as the triple product of its edge length vectors. There's a factor of 1/6. But something that you may not have ever encountered is that you can do the same thing with the area vectors, actually. Simply write any area as the cross product of two edges and work out the triple product of the areas, and you'll find that it's precisely the volume squared up to a numerical factor. All right. So beautifully, this closure constraint that we're seeing plays a dual role in the theory. On the one hand, we're saying determines the local geometry. It's the metrical geometry of, say, a convex polyhedron, but you can use any closed two-surface. But it also is the generator of the gauge transformation. It's the Gauss constraint, right? And we know that's what's happening here because the internal index is also an SU2 algebra index. That was the whole point of it. This was our gauge theory. So this closure constraint generates rotations, and this has a very clear interpretation. The metrical geometry of the tetrahedron doesn't care about how the tetrahedron's oriented in space. That's pure gauge. All we care about is the relationship between these flux vectors, and that relationship gives us the shape, the metrical shape of this region. This actually, stunningly, has to do with a beautiful gauge system description of a cat. I don't know if you've ever heard of this, but if you hold a cat upside down, yes, people do this, you can see the hands at the top there, and you let it go, the cat will turn over. But if the experiment's done carefully, you release the cat with zero angular momentum, right? And that's what our Gauss constraint is saying, zero total SU2 algebra flux. And wonderfully, even though you've released the cat with zero angular momentum, it turns over. How does it manage to do that? It has internal degrees of freedom. It can change its shape. So even though its total angular momentum is zero, each of its pieces can have non-zero angular momentum, and the cat can be described by a gauge theory, which allows it to change orientation, land on its feet, with zero angular momentum. It's a remarkable thing. But that's exactly the metrical geometry we're describing. Tetrahedron is described by its four face areas. They add up to zero. The four face area vectors add up to zero. So the total angular momentum of our shape is zero. But there's enough internal degrees of freedom. That is, we've only fixed 4 of the face areas, not 6 edge lengths, right? Even if we fix the volume, we've only fixed 5 of 6 quantities. So the tetrahedron can change shape without changing area or volume. So this is the gauge system that we're describing here. This is a video I was going to try and play for you, but after yesterday's experience, they said no more videos. So I'll try and load this on my website by tomorrow. It just shows 2 perspectives on this tetrahedron. The phase space turns out to be a sphere. As it evolves around this curve, it changes shape without changing areas or volume. So you can actually see this as a classical dynamical system. Okay. It's time to do some quantization. We haven't done enough quantization of this metrical side of things. But the observation that these are isomorphic as algebraic systems with angular momentum gives us a beautiful strategy for quantization here. We can just leverage your undergraduate quantum mechanics and study the system as irrep spaces. We can take Hilbert spaces, which are carrier spaces for SU2 irreps, and the action of these angular momentum vectors is precisely the action that you're used to. So the electric flux operator acts on a Jm basis as the square root of J times J plus 1 on that basis. The main impact here is that the unit structure of the gravitational field gives us an area outside instead of the h bar that you're used to from angular momentum theory. Well, that area is proportional to h bar, so it's the same in that sense, but it's the g. It carries a g as well. And so this is describing a Planck area. So we get a discrete spectrum for geometry out of this description of the theory. Here you see also the Barbero-Mirzi parameter reappearing in the theory, and its appearance now gives us a physical interpretation. Gamma is we've seen that now that it's got a spectral spacing like angular momenta, and gamma is determining how big the physical space between spectral steps is. So you can think of gamma as a sort of area gap, as fixing the area spacing of this geometrical structure. Of course, it would be wonderful if we could just directly probe whether space-time had spectral discreteness. Unfortunately, you probably know that the Planck area is of order 10 to the minus 70 meters squared. And so you and I are closer to the size of the entire observable universe than we are to the size of these spectral grains. So hard empirical problem there. All right. These JM basis carries, of course, the magnetic index as well. That magnetic index betrays the fact that if we are thinking of one of these facets, it has an orientation dependence in space. But we knew that we wanted to describe the gauge invariant geometry of this grain. So we want to combine each of the facets in such a way that we have a rotational invariant. And the key to doing this is to look for tensors within this tensor product of Hilbert spaces, the 4 facets. Look for a tensor in here that can contract with these JM states and give you a rotational invariant state. So that tensor is known as an intertwiner. It's the one aspect of angular momentum theory you may not have encountered here, although if you studied Clebsch-Gordon coefficients, it's roughly the same idea as the Clebsch-Gordon coefficients. So we contract the JM states with this invariant tensor, and as such, we get the gauge invariant state. This is what I was doing earlier, but I was kind of glossing over it. I said I was modding out by overall rotations at each of the nodes, and this is how we do it. We choose an intertwiner, not just a spin label on the edges of the graph, but an intertwiner at each node. Not only that, but you can choose nice, physically meaningful intertwiner states. So we've been seeing already that the classical geometry of a tetrahedron would suggest that you could introduce a volume operator for each of these grains given by a triple product, and indeed you can make this rigorous. So this has been done very carefully in the canonical literature, where they look at regularization of this operator and carefully check that indeed this gives a sensible operator. But I'd like to point out that even in the 60s and 70s, Levy-LeBlanc and Chakrabarty and company were already thinking about this in the context of angular momentum theory. So one of my jobs that they gave me today was to try and make interconnections. And beautifully, J.J. Carrasco was talking about this huge number of diagrams that we get from double copy theories. Beautifully here, the spin networks are actually doing that same kind of organization of diagrams for us in the theory. The spin networks are taking all these graphs and organizing them into nice pieces where we can pick out physical basis states like this with the volume and the areas labeling the intertwiner and the facets. All right, I am gearing up for the last part of the talk. And I'm going to make a change of notation here. I'm sorry for this, but I struggle to keep consistent notation throughout the whole thing, so I'm just going to do it explicitly so you see me do it. Up to now, I've been putting emphasis on the Ashtekar electric field, the fluxes, and I was careful not, to call them electric fields and not something related to area because we also had the Ashtekar connection in the game. But at this point, it's going to be convenient for me to switch notation. I'm not going to be using the Ashtekar connection so much in what follows, and so I'll shift from calling these E vectors to calling them A vectors to more directly give you the intuition that their magnitudes are equal to areas. At the same time, I'm also going to give you labels for the different pieces of our tetrahedral grains. The edges I'll call E, I'll label with indices E, the triangles with indices T, and the tetrahedra with indices tau. All right. That's all set up for the spin foam approach we're about to take. But before I go there, I was asked to also tell you about some of the things I've been doing in my own research. And this connects nicely with Bianca's overview talk that she gave on the first day. I want to emphasize that this setup is extremely well positioned to deal with both Euclidean and Lorentzian geometries. And here's one way of formulating that. You can check that the Minkowski theorem works just as well whether you're working in a SU2, SO3 is isomorphic to SU2 as an algebra, of course. So whether you're working in the Euclidean context or in the SO2-1 context, in both cases, closure describes the algebraic structure of a closed geometrical polyhedron. In the latter case, you may not have been used to thinking about a tetrahedron. We mean a space-time tetrahedron here. So one way to think about this is you and two of your friends are playing soccer in a big parking lot, and the soccer ball happens to be between you somehow, and three of you run at the soccer ball at the same time, and you end up meeting at the soccer ball. That would be a tetrahedron in space-time, right? You're separated spatially by a triangle. As time evolves, you come together to a point. So that would be a Lorentzian tetrahedron. That tetrahedron has the same space-time description as the Euclidean tetrahedron I was just explaining for you. Not only that, but beautifully you can cast the volume that we were just studying, this triple product, as a determinant, and if you like, you could square that, and the determinant squared, well, that immediately leads you to a so-called Gram matrix, a matrix of dot products between these vectors. And the leverage that you gain by doing that is that this dot product, I can interpret it as being in a Euclidean R3, and it's just the standard Euclidean tetrahedron you're used to. But if you like, I can also interpret it in a Lorentzian R21, in a Minkowski space. And when you interpret it in that latter way, you find that, well, taking determinants, I would have to insert the determinant of the Minkowski metric in the middle here. That would just give me a minus sign. And the sign of v to the fourth, oddly, v to the fourth, this is not something we're used to, the sign distinguishes whether you're talking about a Euclidean tetrahedron or a Lorentzian one. So this is actually beginning to go into this interesting world that's been opening up in the community in the last year or two of working with an area metric. This Gram matrix is the simplest possible example I know of a so-called area metric. It's where we're studying the geometry of these grains via the areas instead of via the lengths. This is very much in harmony with the symplectic structure of general relativity. It's why we're doing this, why people are pushing in this direction. So something wonderful that I've been working on is that using these area variables, you can cast this volume. You just take that determinant we were looking at, and you can cast this volume as a cubic in the couplings A12, A23, and A13. If you work in those variables, you'll quickly see that actually the sum of these three couplings is precisely the sum of the four area squareds. This is a quick calculation. But if I combine these two algebraic identities, I have a cubic curve in the plane. And remarkably, cubic curves in the plane are one of the most mathematically well-studied objects in the whole of geometry. These are known as elliptic curves. So what we've just shown is that there's a correspondence between tetrahedra and elliptic curves. And this gives us a new tool for the field that I'm really quite excited about, because elliptic curves are one of the places in which Diophantine analysis of geometries that have integer solutions, are best worked out. So suddenly the quantization conditions, which make these angular momenta into integers or rational numbers, those quantization conditions are suddenly very harmonious with the geometry of elliptic curves. And what's particularly stunning to me here is that you couldn't have done this unless you had appreciated that both Euclidean and Lorentzian geometries contribute to this. So the correspondence with elliptic curves wouldn't be complete unless you allowed for the Lorentzian signature. So we have an avenue now for kind of classifying all quantum tetrahedra in space and space-time via their elliptic curves. If you haven't ever studied elliptic curves, I understand. It was an area I avoided, but you should know that this was at the heart of the proof of Fermat's last theorem. So that's a beautiful example of the way in which they interplay with Diophantine problems. Not only that, but something that's really striking about elliptic curves is they have a geometrical construction of a so-called group law. It's an abelian group law, so people often represent it as addition. But the idea is very simple. You pick a point on the elliptic curve. You can take the tangent to the curve at that point. Because it's a cubic curve, it will intersect at a unique second point. And by taking the vertical through that point, you construct what's called the addition law on the cubic curve. This is the doubling. Because I took a tangent, it's giving me the doubled point 2p. But you could also take something that goes through the curve, not the tangent. If you took 2 points on the curve, you took the line through the two, you'd get a unique point. You reflect, and you get the sum of those 2 points. So this defines a mathematically precise group law on elliptic curves. And now we have a remarkable interpretation of this in quantum gravity, which is that you can add tetrahedra. So there's a group law, a well-defined mathematical group law. And in particular, what I find interesting in this case is you can add 2 Euclidean tetrahedra, and you end up getting a Lorentzian tetrahedron. So I don't know how to interpret this in the quantum theory yet. This is work in progress. But I'm just trying to illustrate the ways in which the correspondence with an elliptic curve is going to be an interesting tool for thinking about quantum geometries. All right. So the last part of the talk, I'll try to give you an overview of the path integral spin foam approach. I'm going to take, as I said, a non-standard path to this. I'm going to introduce you to what we call effective spin foams. One of the reasons I'm doing this is that they highlight a feature of spin foams that I don't think is always highlighted, and I think it's a good thing to expose people to and to get your thoughts on. The approach I'm going to take is going to go through what's called Reggie calculus. Reggie calculus was invented in the 50s and 60s by Tullio Reggi. And the idea is to describe curved spaces by giving piecewise linear approximations to them. So if you think of a two-dimensional surface, I chose Mount Rainier because I went to college. I went to Reed College, and Mount Rainier was out our back window. So this is a beautiful landscape. And Scott Bailey made this wonderful picture. I don't think he had Reggie calculus in mind, but this beautiful painting of Mount Rainier you can see here is in a Reggie formulation. So the idea of Reggie calculus is you take these piecewise linear regions, and instead of completing this into a flat plate, you remove one of the triangles and identify the remaining edges, and this concentrates curvature at the pink dot. It's easy to get confused here between the intrinsic and the extrinsic curvature. The embedding means nothing in this picture. I'm not talking about the curvature between these two triangles. I'm talking about the intrinsic curvature. If an ant parallel transported a vector as it went around this point, it would find a concentrated curvature at this tip. But you can do this at every dimension, and there's a rhyme with what we saw in the canonical theory, which is that you have a choice to make. You can work with edge length variables, that is the standard metrical variables. But if you do that, the canonically conjugate quantity is a disgusting mixture of angles and very hard to parse. The alternative is to work with the area of triangles, with the area variables that I was describing for you. And if you work with those area variables, well, then the curvature angle, the codimension 2 surface is a triangle, and the curvature variable is just the angle that you get on parallel transport around that triangle. So this is a beautiful harmony with loop gravity. It's much nicer to work with the area variables in Reggie calculus. So I'll do what we call area Reggie calculus. And in area Reggie calculus, there's a problem right at the outset. And it's a problem that actually confused our community for quite some time. Luckily, I think it's been clarified a lot in recent years. So in the standard length Reggie calculus, where you treat the edge lengths as your variables, you get good equations of motion. That is, as we refine the graph that we're studying, we recover the Einstein equations. But if you work in area variables, the Reggie action is actually quite simple. It's simply the product of your areas with the deficit angle at the bone. The deficit angle is just defined as 2 pi minus the dihedral angles as you go around that bone. So it's really measuring that deficit that we were seeing in the first picture. And we can cast that deficit angle as functions of the areas. So we're just thinking of these dihedral angles as functions of the areas. If you aren't sure how to do that, you can just go through the length variables. So you invert the length variables for the area variables and recover the dihedral angles that way. But the trouble that you run into is that when you take the variation of this discrete action, well, you get the curvature, and then you actually immediately have a classical differential geometric identity called the Schlafly identity that kills this second variation. That is, for all geometries built this way, this term is 0. And so your equation of motion becomes that your curvature is 0. So this is a disturbing aspect of area Reggie calculus. that caused people a lot of concern. They were worried that spin foam theories that are built on area variables might just always be flat. But there's a way out of this. And the way out of this is to think carefully about how we're gluing these four simplices. We want to build up a triangulation of a four manifold. And the way you glue two four simplices is you pick a tetrahedron. Say the tetrahedron picked out by these four orange dots. And we're going to glue it to a second tetrahedron. In a length regicalculus, you're gluing 6 edges, and they just geometrically match. Everything is fixed, and you can't go wrong. But if you're using area variables, those two tetrahedra only have 4 area variables. And it's clear that when we glue, we're not fixing the geometry of the two tetrahedra. Just getting the areas to match isn't fixing their Euclidean geometry. And so this does somehow have more flexibility than you would get from a length regicalculus. And so the strategy is to introduce more variables to make sure that the gluing is somehow good. So what we do is we work with that area gram matrix I introduced you to before, that we simply include 2 more variables in the theory, the dot products of 2 of these normal vectors. And now we have 2 of the dihedral angles. It turns out that you have to be careful. They have to be 2 edges that are non-opposite in the tetrahedra. But if you include them as variables, you can impose a nice constraint on the theory that makes these 4 simplices glue well. Nonetheless, there's a catch, as there always is. And the catch is that if you look at the Poisson structure of that tetrahedral gauge theory I was telling you about, you'll find that those 2 dot products that I just introduced you to, they don't Poisson commute. Their Poisson bracket is proportional to the volume, where the plus or minus sign here has to do with the Euclidean or Lorentzian geometry. So this set of constraints is second class. And you probably know that if you can't impose a second-class constraint strongly. And so you have to be more careful about how you impose this. You have to impose these constraints in a weak manner. So this is at the heart of what I wanted to tell you about spin foams, and that I think is something that the community is appreciating more and more right now, which is that whether you make it implicit or explicit, always behind your spin foam theory is some gluing rule, some way in which you're matching tetrahedra, and often that way has subtleties embedded within it because of this non-Poisson commuting aspect. All right. So just to tell you finally how we define the spin foam, again, here's the deficit angle formula we were looking at before. You plug it in. It's easy to include boundary triangulations. I just include an index here that is either 1 or 2 if the triangle is in the bulk or on the boundary. And then you can nicely split up the area regicalculus action into a piece that's a sum over triangle and a piece that's a sum over simplices. And the 2 pieces are defined down here. And here's where the quantum ingredient comes in. So there's 2 things. The emphasis I was just giving you, here's the regicalculus action, but we are going to add in a piece, which is our gluing constraints. So that's where in the action we've encoded the gluing constraints. And then the second thing is that we're going to add in the quantum piece now, which is to use these area spectra that we just saw earlier in the talk. So this is what's going to turn this into a partition function path integral model. And we have to be careful here. Bianca used this analogy early in our work together, and I fell in love with it. We have to navigate very carefully between 2 dangers. If we impose the constraints too strongly, we're going to have an issue of, so this spectrum, of course, doesn't allow every area. You only have the spectral spacing that you have. And because of that, if we impose the constraints too strongly, we have a hard Diophantine problem. It's coming back here, right? That's why I was emphasizing the connection with elliptic curves. The hard Diophantine problem is to find geometries that satisfy those constraints. We may just run out of all of our density of states. And so we can't actually perform the path integral. So we have to impose them weakly enough that, that there are some geometries that satisfy them. On the other hand, if we impose them too weakly, we won't get the right dynamics out of the theory. right? That we saw that we needed the constraints in order to get the area-Reggie action to have good classical equations of motion. So this is the twofold, the Charybdis and Scylla that we're navigating between. So what is an effective spin foam? I can define it now. It's a sum over these spin labels on our triangulation with a measure factor, amplitudes due to the triangles in the area-Reggie calculus action, amplitudes due to the simplices in that action, and the gluing constraint piece. And the idea of the spin foam is to try and go over all such triangulations, all such labels, I should say. So the way that an effective spin foam achieves this weak gluing, this weak constraint, is by choosing coherent states that are peaked on good dihedral angles, but don't strongly impose those dihedral angles, so that we still have enough density of states. So that's the idea of the theory. We make several numerical approximations in order to study it on a computer. So we consider symmetry-reduced triangulations. That is, we're going to consider configurations where a bunch of the areas are equal just to make it easier to compute the thing. We approximate the coherent inner products by real Gaussians. This is an even weaker implementation of the constraints where we just say, okay, we're going to take it to be Gaussian peaked around the good dihedral angle. And the wonderful thing is that we can show on a laptop in a matter of hours instead of weeks and days, we can show that there's a good semi-classical regime of the dynamics when we scale with both the area spectral gap, gamma, and the spin labels. This has become a huge community of people working on these things. I've included everybody that's working on both the effective spin foams and on the area metric geometries here, so I'm kind of blurring lines a little bit. But Bianca Dietrich's group and many of her students and postdocs have been working on a lot of these things. I'm going to just show you one numerical example. It's actually an old example. I figured that most of the people at the conference will be, most of the people that are working on these things will be presenting much more recent results, so I think I would just present the one that I was involved with. This was a symmetry-reduced triangulation that has an internal edge and hence has gravitational dynamics. This triangulation consists of 6 four simplices, and it's a symmetry reduction. And here I'm describing that reduction carefully, but I'm running low on time, so I'm not going to go through it in detail. Here I'm giving even more details where you can see which areas are identified in the symmetry reduction. But the main point that I want to give you is that in a classical length Reggie calculus, you can find the deficit angles around, say, these areas, this area as well, and you get these values in the length Reggie calculus. And in our spin foam model, you get complex deficit angles. That's expected because we only impose the constraints weakly, so there should be some violation. But you can see that quite nicely, these are in excellent agreement up to the small violations that are coming from the weak imposition of the constraints. So this is beginning to make spin foams a very computable approach. The Lorentzian EPRL models are also becoming computable, but they have to use very computing intensive codes in order to do the full summation over the spin foam, and here you can do this on a laptop. It's really a much faster model. It's very approximate in the sense that we use these coherent states to impose the gluing, but the beauty of this approach and why I was putting so much emphasis on the gluing constraint is that that every spin foam model should have some gluing constraint. So you could go to EPRL, and if you worked it out carefully, you could figure out what its gluing constraint is, and you could approach EPRL from the same perspective. It was this that we had in mind when we called these effective spin foams, but you could also think of these as a fundamental, excuse me, a fundamental model for quantum gravity. So just to summarize very briefly, you can think of an effective spin foam as being roughly made up of 3 pieces. There's a measure factor. I didn't talk about this at all, but the expectation is that that measure factor would come from thinking about coarse graining of your triangulation or careful treatment of diffeos in an approximate Reggie-calculus sense. The area Reggie action is what we use to actually make the action of the theory, and then these gluing constraints, which is where I wanted to put the emphasis on this spin foam model, impose the good dynamics of the theory. Thank you very much.
Thank you, Hal, for this beautiful overview talk. Questions? I'll be running up.
Can you comment on the problem of corresponding loop space results to the results that those of us who do covariant quantum gravity perturbation theory calculations obtain?
So there's a couple of things that I can mention just very briefly. So you can compute in this spin foam approach, you can compute, for example, the graviton propagator. You're computing it at lowest order. Or another way of saying it is these spin labels, as you think of them as large, you're taking a sort of semi-classical limit of the theory, right? If you think of J over H bar, then the large J limit is a large action limit. And in that limit, the lowest order in the graviton propagator agrees with perturbative. In what background? I mean, this would be in a flat background. So that we're taking a 4-simplex model, and so we would be thinking of it as a flat background. I should be careful in how I say that because the background is sort of emerging as the semi-classical limit of that propagator. But there's much more to be done and connected between the perturbative theory and this loopy approach, right? Because the loopy approach doesn't want to work on a background. You want the background to emerge from the dynamics. And so as a non-perturbative approach, there's much to be done to further connect the coarse graining of that. The result I just told you is on the extremely simple triangulation. So you'd like to coarse grain that and see more thoroughly that you're working on a background of a standard perturbative sort. So this is very much an area where the understanding of the renormalization of the theory needs to come in to give us a stronger connection. That said, recent work that Bianca's done on the linearized theory in these area metric variables shows that in the linearized theory, you have a really good connection with the standard perturbative results on flat backgrounds, for example.
Thanks for this very nice overview. So something that struck me was the prominence of the Euclidean tetrahedron. So I'm wondering, isn't there a bit of tension between this exact Euclidean structure and the search for UV gravity? I mean, should we think of this tetrahedron as being something fundamental, or what is the connection?
Thank you very much for this question. As part of the International Society of Quantum Gravity, I just gave a course in the basics of quantum gravity, and I give many more details there, and I really go deeply into this question, but I had too many tasks to do today. And no, I do not think they're fundamental at all. So one place that I was trying to emphasize that was when I was saying that these should be thought of as fuzzy tetrahedra. We are fixing only 5 of the 6 classical parameters, right? And as such, the quantum state that you're talking about is spread out over that whole 6th parameter. So no, you should definitely not think of little tetrahedra at the bottom of space-time, right? This is like a coarse graining. I'm working with a finite number of degrees of freedom. Which ones? The dihedral angles between 2 faces and the areas of the faces and the volume maybe, right? Those are the ones that I described at various times in the talk. And those are, it's like, you know this beautiful picture of Baez and Buns, of seeing the Einstein equations as I take a ball of test particles and I use the central particle to give me a proper time, and I measure how the volume of the ball changes in time. And that is the Einstein equations. So that's a beautiful picture. But they have an infinite number of particles to give that description, test particles, right? This is like I have 4. I don't have an infinite number. I'm describing a hugely truncated set of degrees of freedom, right? A tiny little subset of all of the gravitational degrees of freedom. And I'm only using this truncation because I can work with it mathematically and get a leverage from it. So we definitely need to understand what it means to refine this geometry.
But still, the relations between your variables are set, in a sense, exactly by the Euclidean tetrahedron. This is what you're using as a starting point. So one can argue or discuss whether these relations are indeed the simplest ones to work with. So I wonder whether this, is the strategy clear that one should be sticking to the variables of the Euclidean tetrahedron, even though you say we should be fuzzy?
I was very careful to say it's not just Euclidean, right? It's Euclidean and Lorentzian. And maybe another sort of piece of work which I referred to during the talk, but I can mention now in more detail, Laurent Friedel and Daniele Pranzetti and Mark Geiler and company have been looking at this kinematics of these surfaces in the continuum theory, the two surface. We call it the corner, right? Because you're imagining two Cauchy slices in space-time meeting at a corner. At that corner, you can study this two surface, and you can study the kinematics of that in the continuum theory. And beautifully, they obtain a fluid description of that. And the fluid description can be quantized. And the density of the fluid on the boundary surface is describing the area variables. So even at the level of the continuum theory, you're getting that same structure emerging. So do I think the tetrahedra have answers to everything quantum gravity? Absolutely not. Profoundly not. They are a coarse graining, right? It's just a coarse graining that you can get a handle on and that you can understand the basics of the theory from. But there's a lot of work that's happening now that's very exciting, that's connecting these pictures, right? That's not saying that they're totally remote from each other, that you can actually work with the Casimir of the diff S2, the diff of this corner region, and that Casimir is giving you the same sort of description.
Thank you very much, Hal. That was great answers, great questions. Let's thank him one more time. So before moving on, again, can I ask everyone to squeeze a little bit more to the middle? There are quite a few people on the sides, especially on this side. I think there's lots of room. So if you guys all move to the side and people can move more to the inside. If you're really set on sitting on the outside, can you please stand up and let other people pass by? Because we'll get into trouble with, the firemen and everything. So no one is allowed to sit on the stairs. No one. Great. There's also the front row here if you really like to. Great, thank you all for making space for everyone. Great. So having said that, time to move on to the next talk. So we have Madhavan who will be teaching us about the same themes, and there's lots of interesting things to say, but I just wanted to say that I think I saw on the internet one of the cutest pictures of a research group, by his group. Just go look online. There's really a very cute picture of absolutely, I think, the youngest research group, I might say. It's quite adorable. In any case, on to science. The floor is all yours.
Thank you. Hey, thanks a lot for the introduction and advertising my precocious research group. So first, I'd really like to thank the organizers for giving me this opportunity to speak about some new results. So what I'd like to do is to share some new results which pertain to the construction of a dynamics for quantum gravity. And I'll work within the canonical quantization approach to quantum gravity, which is known as loop quantum gravity, and which you heard about in the first part of Hal's talk, which just preceded this one. So what I'll do is I'll begin with some introductory remarks, which will serve both to review the relevant background as well as to set a proper context for these new results. And so let me start with a review of how we understand dynamics in the classical Hamiltonian formulation of, say, vacuum gravity. So we have a space-time manifold M with a space-time metric little g. The Einstein equations are satisfied here. The space-time is topology sigma cross R. There is a there's a time evolution vector field on this space-time, and slices of constant time are all diffeomorphic to sigma. On each such slice, the space-time metric induces a spatial metric Q, and this Q serves as one half of the phase space variables. The other half is called P, and that encapsulates information about the extrinsic curvature of this slice as embedded in the ambient space-time. Dynamics along this vector field is generated by a Hamiltonian. So what the Hamiltonian does is that it evolves data from one slice to another, and that is what evolution is in the classical theory. One can then solve the Hamilton's equations, and then one gets a one-parameter family of these Q's and P's, one for each slice. And from this one-parameter family, one can then reconstruct the space-time metric, which then goes and satisfies the Einstein equations, and that closes the circle. It's useful to decompose the time flow vector field into components normal and tangential to the slice, and these are parameterized by the lapse and the shift. So the shift is tangential to the slice, little n is the normal to the slice, and the lapse is the amount which you go normal. The Hamiltonian then resolves into a sum of two generators, one which generates the evolution normal to the slice, and which is called the Hamiltonian constraint, and the other which is generating transformations tangential to the slice, and that is called the diffeomorphism constraint. And of course, it's so called because what it does is that it turns out to generate three-dimensional diffeomorphisms of this data. So the non-trivial evolution out of the slice is really governed by the Hamiltonian constraint, and so in the quantum theory, the corresponding Hamiltonian constraint operator is what controls the dynamics, and hence its construction lies at the very heart of canonical quantum gravity. This classical constraint is a very complicated function of the Q's and P's, and I think one briefly encountered it in Klaus's talk, maybe on Monday. And it's complicated both for Lorentzian and Euclidean gravity, and therefore it has resisted attempts at a rigorous quantization. I'm going to focus on the Euclidean constraint for reasons which are going to become clear shortly. Now, while the Euclidean constraint is a very complicated function of the Q's and the P's, it acquires a very simple form in the Ashtekar-Barbero variables, the real ones which Hal talked about. And the simplicity of form is what makes it then much more amenable to quantization efforts. So what are these variables? Let me review from Hal's talk. These variables are an SU2 Lie algebra valued electric field. So the index A is a tangent space index, and little I is a SU2 Lie algebra valued index. And there is a conjugate connection, which we call A. So since the Lie algebra of SU2 is three-dimensional, we have EA1, EA2, EA3. So there's a triplet of spatial vector fields, and these are interpreted as a spatial triad. and this then, from the spatial triad, you can then go and construct the metric. So the E's contain all the spatial metric data, and therefore the conjugate variable A has the extrinsic curvature information. So this is just as Hal also reviewed. The Hamiltonian constraint then takes a very, very simple form. So it's an integral over the spatial manifold. There is a factor of the lapse, and there is a polynomial term. So there are two E's and an F, where F is the SU2 curvature of this connection. And then you have a non-polynomial piece, which is 1 over square root of the determinant of the 3 metric. And remember, the 3 metric is constructed from the E's, so this is actually a function of the E's. And this non-polynomial part is there so as to render this integrand of density weight 1 so that you can integrate it without trouble over the spatial manifold. So our aim is to construct the corresponding quantum operator in the LQG representation which Hal introduced. Okay. Now, since in GR space-time is itself dynamical, there is no preferred background. All background objects are fictitious and unphysical, and the guiding philosophy of LQG is that it aims to construct everything, and in particular the Hamiltonian constraint operator, without relying on any fictitious fixed space-time background structures. And this kind of quantization or setting up quantum field theory in the absence of any space-time requires new ideas and techniques beyond those which have been developed so well for quantum field theory in a fixed and often flat space-time. So these ideas and techniques were developed by a huge number of people, I guess, out of which Jurek Lewandowski was supposed to be here but is not, and Renata, she hasn't bunked my talk, is also somewhere around here. Here she is. Okay. And so all these efforts then culminated in Thomas Thiemann's construction of the Euclidean constraint operator in his quantum spin dynamics work. Thiemann also showed in that work that one could construct the constraint operator for the Lorentzian theory from the Euclidean constraint and the volume operator. And the volume operator we know is defined in LQG. This was a big theme of Hal's talk. And so the first step in this business is to actually focus on the Euclidean constraint operator, and then we can go and construct the Lorentzian one. And this is why I'm restricting in this talk my attention to the Euclidean Hamiltonian constraint operator. So the QSD construction of Thomas was of this Euclidean constraint operator was and is a spectacular achievement. However, some open problems do remain. There are many ambiguities in the final operator action, and I'll come to this soon. And secondly, the constraint commutator between a pair of Hamiltonian constraints does not reproduce the correct lapse dependence of the operator correspondent of its Poisson bracket. And from classic and beautiful work of Hodgman, Kukash, and Teitelbaum in the 70s, this particular dependence of the lapse turns out to be intimately connected with the implementation of space-time covariance in the quantum theory. So this is quite important. In our view, further progress on these two issues was handicapped by the absence of any intrinsically three-dimensional interpretation or intuition about what this classical evolution constituted. So just to remind you, for the diffeomorphism constraints, one exactly has such an interpretation. The diffeomorphism constraints just generate three-dimensional diffeomorphisms of this phase space data, and capturing that intuition or that geometrical interpretation in quantum theory is really what allows one to represent in LQG the diffeomorphisms correctly as unitary operators. So the hope is that perhaps if one had a little bit more intuition about what the Hamiltonian constraint does in purely three-dimensional geometric terms, maybe we could feed that and imprint it onto our constructions in the quantum theory, and thereby perhaps make progress on these two issues. So this brings me to the main take-home message of this talk, which is that classical gravitational evolution in time, which is generated by the Hamiltonian constraint, can now be reformulated or thought of in terms of certain spatial diffeomorphism-like transformations. This is a bit vague, but will become clear in the next slide. And these transformations are generated by a triple of shift vector fields. So these are spatial vector fields constructed from the electric field data. This classical insight dovetails naturally into a new construction of the Hamiltonian constraint operator for Euclidean gravity, in which these diffeomorphism-like transformations of quantum states associated with this electric field play a key role. And this new Hamiltonian constraint operator then has improved properties both with regard to the issue of ambiguities and space-time covariance. It doesn't offer a complete solution, but it does have improved properties. So let me now turn to an account of this new classical insight. And in order to do so, I'll just make a very brief digression on Lie derivatives and their gauge covariant counterparts or generalizations. So consider a Lie derivative of a Lie algebra valued vector field. So here again, the little I is the Lie algebra index with respect to an ordinary vector field V. So one can just write down the usual expression, and then one notices that under rotations, gauge rotations of this index I, this object is not gauge covariant. So if you want to make it gauge covariant, there's a simple way to do it. Given a connection, you can just replace the ordinary derivative by a gauge covariant one, and then this of course is gauge covariant. And at least to my knowledge, this was first written down by Jacques, who also is no longer with us, way back in the early 70s, I think. And there is a nice geometrical interpretation of this object, and it really corresponds to infinitesimal translations along the horizontal lift of the integral curve of V to the principal fiber bundle. Now, what if this vector field V also was Lie algebra valued, that it had internal indices? Well, one can define just by analogy an object which we can call a generalized gauge covariant Lie derivative, and which is basically just, since this object has an internal index, now we just in both instances replace this by the gauge covariant derivative. So this also depends on the choice of a connection, and the exact geometrical interpretation of this, unlike the gauge covariant Lie derivative, this geometrical interpretation is still open. So while one doesn't have an exact geometrical interpretation, yet there is probably some very rough, vague intuition that this object has something to do with some sort of transformations which are associated with this Lie algebra valued vector field. And that's all I'm going to use to motivate what I'm going to do in quantum theory. So now let me, after this brief digression, go back to general relativity, and from the electric field data and the laps, I can define up to some other factors which I'm not going to get into. I can define something which I call the electric shift. So this is a Lie algebra valued vector field because of this index I, and then it turns out that the evolution equations generated by the Hamiltonian constraint on the constraint surface take a really intriguing form, which is that the time derivatives of, say, the electric field and the curvature are just written directly in terms of combinations of these generalized gauge covariant Lie derivatives with respect to the electric shift of the fields themselves. So, of course, this depends on the connection, and the connection is the second part of the data. So you have the electric shift, which depends on the electric field, and the connection creeps in from the definition of the generalized gauge covariant derivative. But nevertheless, this is really a beautiful and extremely intriguing form, and I just wanted to exhibit it over here. And therefore, the message for quantum theory is to try to encode the action of the Hamiltonian constraint operator now in terms of transformations which are generated by the electric shift, which now becomes an operator because it depends on the phase space variable, which now becomes an operator. So that is the aim of what I'd like to do. And let me then go on now to quantum theory and just quickly recap, maybe in a slightly complementary way, what Hal did. So let me very, very quickly in 2 slides tell you about the quantum kinematics of LQG. So it's a connection representation. Wave functions are functions of the connection. The basic connection dependent operators, as Hal pointed out, are holonomies along edges in the Cauchy slice. So if you give me an edge in the Cauchy slice, I can integrate the connection one form over the edge like this, and there is a path ordered exponential which you write down, which is gauge covariant, and in order to actually go and sum the series term by term in this exponential, you need to use some representation of SU2. So this also involves implicitly a spin representation of SU2, so j equal to half, 1, 3 by 2 or whatever. So the holonomy operator then just acts by multiplication. So you have wave function of the connection, and then this acts simply by multiplication over here. So you get a new function of the connection. And the triad operator acts by functional differentiation. And here you have the factor of g, which comes from the symplectic structure, which reminds you that you're in quantum gravity and not in Yang-Mills theory. States are linear combinations then of, you can go to a basis of states, and in this basis states are linear combinations of products of these edge holonomies. So if you draw an edge holonomy over here, you also have to color it with the representation in which it's evaluated. So you have like a pink edge over here, which might be j equal to 5, and a purple edge with j equal to 3, etc. And so the collection of all these edges in the product form a graph, and therefore you have a colored graph over here. And if you take the action of the holonomy operator, and let's say that we construct, we're interested in the action of the holonomy operator when the edge is a loop, then what it does is that it multiplies the product, so it also comes and joins the product over here, and therefore this edge is added to the existing edges of the graph, and so you just add this edge over here. And you can see that the new graph then has some extra vertices, and then there is a place where the purple and the black edges overlap. So this over here is a multiplication of an edge holonomy in the black representation and the purple representation. Then you can use Clebsch-Gordon decomposition to just write this in terms of sum over angular momenta representations, and the end result then is a sum over these colored graphs, which are uniquely colored. So every edge has a unique color. So that's how the holonomy operator acts. The operator which is of interest for us is the volume operator, and that is constructed from the triad field. And it turns out, Hal hinted at this, and it turns out when you actually regulate it and then take the regulator away and write it down rigorously, the action of the volume operator on one of these colored graph states is only non-trivial at its vertices. So if you have a volume of a region R, and if that region intersects a vertex of this graph, or contains a vertex of this graph, then you get a non-trivial contribution. If there are no vertices in this region R, then the action is just trivial. It annihilates such states. So much for the kinematics. What about the evolution? Well, first the tangential evolution along the slice, which is a diffeomorphism. And it turns out, due to the background free quantization, that diffeomorphisms turn out to be unitarily implemented. And their action is very simple. What a diffeomorphism does on one of these colored graph states is that it just moves it along by the diffeomorphism, preserving the edge colors. So now let's go to the Hamiltonian constraint, which is the quantum dynamics normal to the slice. And recall that the Hamiltonian constraint for the Euclidean theory was just some polynomial part, and then there was a square root of q dependent factor. Recall also that the volume is built from this square root of determinant of q, and then it turns out that just like the volume operator, the square root of q operator also acts only at vertices of states. So with appropriate operator ordering, the Hamiltonian constraint action is then just a sum over vertex contributions, and at each vertex we then need the action of the curvature operator. And this actually presents us with the following absolutely key problem, and which underlies, this is really the heart of the problem which we face. The problem is that the curvature is a local function of the connection, whereas the basic connection operators are non-local holonomies. So classically, there's no problem. One can just extract coordinate components of the curvature from taking a small coordinate size delta loop, right? And then you can just verify. You take the holonomy -1 divided by the coordinate area of the loop, take the limit delta going to 0, and you'll get some suitable coordinate components of the curvature. So what do we do quantum mechanically? Quantum mechanically, one looks at the expression for the Hamiltonian constraint and replaces the operator by this regularized expression, and then tries to take the delta going to 0 limit of the Hamiltonian constraint, whatever the expression is. So the good news when we do this is that one can actually define this limit, take delta going to 0, and hence we can define a constraint operator. But the bad news is that this final operator action, unfortunately, depends on the choice of small loops, so what its shape is, how it interacts with the graph state it's acting upon, and it also depends on the representation or color of its holonomy. And this is really the problem of ambiguities, which will become even more clear on the next slide. So here, I home in on one of the vertices where the Hamiltonian constraint is going to act. And typically what happens is that the choice of loop is dictated by simplicity, and the representation of the loop is taken to be j equal to half. So skipping over some technicalities which are related to taking this delta going to 0 limit, an accurate pictorial representation of the essential features of this operator action with these choices is as follows. What happens is that the Hamiltonian constraint, because of the determinant of Q factor, comes and homes in on the vertices. And then at each vertex, one adds a loop, which is a curvature approximant. And the simplest choice of this loop is to make it a triangular loop. So choose two of the pre-existing edges of the graph and construct two parts of the loop from them, and then close it with what is called an extraordinary edge. And then color it with j equal to half. So you can see that if j was not half, it was some purple, pink, blue color, right? Then you would get a different colored graph. And also if it wasn't triangular, but it went and it interacted in some way with the other edges of the graph, you would again get a different kind of result. So, and then of course you sum over all contributions with all pairs of edges, but nevertheless this is really the source of the ambiguities in the final operator action. So let's see now how we can alleviate this a little bit by moving on to these new results. So what is the new construction? So recall that in the classical theory, we were asked to focus on the electric shift. So let's do this in the quantum theory as well and see what happens. So recall that the Euclidean constraint was just this n, e, e, f, and the square root of q dependent factor. And this n times e is already the electric shift. So it's sitting right there in the operator itself. And in quantum theory, this ne becomes an operator, the electric shift operator. Again, the square root of q dependent factor yields a sum over vertex contributions, and so we have the electric shift operator which acts at each vertex. Now the simplest objects, if you notice, this has a certain structure with a tangent vector index over here, and the simplest objects at a vertex with this sort of an index structure are just the edge tangents. So what happens in detail is that this operator pulls out factors of edge tangents, and when all the dust clears, the constraint action becomes naturally implemented in terms of diffeomorphism-like translations along the edges at the vertex. So supposing I fix a particular edge and call the diffeo-like translation along that edge by phi e, then this is roughly what happens pictorially. So phi is, we call an electric diffeomorphism because it came from the electric shift. And it turns out that the small loops which encode the curvature operator are now built from the action of this phi e on the remaining edges at the vertex. So let's fix the blue edge over here. We have this vertex. Let me fix this blue edge to be this edge e. And let's look at one of the remaining edges, say the brown edge. So what this guy does is that it pulls this edge up in a diffeo-like manner and creates this edge. And if you look at what the corresponding loop is, then it has exactly this segment over here, and then you go along the original edge, the original brown edge, and you close it going along this blue edge over here. And because it's a diffeomorphism-like transformation, it doesn't change the labeling of the brown edge, so the loop is in the brown representation. So what has happened is that the labeling ambiguity, whether it was j equal to half, 1, 2, is now gone. The labeling is just attuned to the particular edges of the graph, which are already existing, what their colors are, and then the shape of the small loop is really determined by the way these electric diffeomorphisms act. Okay, so that's what I've said again. The color ambiguity is fixed. The geometric understanding of shape is now there in terms of what these electric diffeomorphisms do. And one also gets the correct lapse behavior. In fact, in detail, one can show that on a suitable space of states, that the commutator between two Hamiltonian constraints is anomaly free, so that you get exactly the operator correspondent of its Poisson bracket. And this was one of the ingredients for the emergence of space-time covariance from the canonical theory. So just to summarize, I'm almost done. This is sort of the technical part, and the new results are now over. I'll just summarize. There are still ambiguities which remain, but the Hamiltonian constraint operator action is certainly better determined. It beautifully implements our classical intuition, and in passing, it seems closer to its detailed physically appropriate implementation in mini superspace quantization, known as improved LQC, and in my view constitutes exciting progress. I started 5 minutes late, or 7 minutes late, so I will just flash a couple of slides and then stop, because I was asked to also comment on problems for the future, at least as I see them in the canonical theory. So one is, of course, to now try and apply this new dynamics to mini and midi superspace contexts. There's another very interesting subject to probe, and this is the transition to Lorentzian theory, and this is due to an old idea of Thomas, where he constructed a complex canonical transformation which led you from the Euclidean self-dual variables to the Lorentzian ones. And he also suggested a way to implement this in quantum theory, and once you do that, you can actually take solutions to the Euclidean constraint, apply this operator, and rotate to solutions to the Lorentzian constraint. So this is a beautiful idea which I think deserves further study. Let me flash a few references over here, and then this was my final slide, and I can either go through with it or I'm done, and you can read it as you wish.
We have time for one question. How about that?
Sorry?
Let's go for people reading it, and
Okay,
then we
sure.
have time for questions.
Sure.
Thank you very much. So, anyone? Yes, we have one up there. Okay, on my way.
So, what do you mean by the action of this commutator is represented on a suitable set of states? What do you mean by suitable in terms of spin nets or group
so
averaged?
There are certain distributional sums of spin network states, right? So which they have to be off-shell, so they can't satisfy the constraints, otherwise you'll just get 0 equal to 0. So there's some off-shell distributions which one can construct, and on this large set of states, one can show that this constraint algebra is satisfied. So the actual definition is quite technical, but it's basically some set of off-shell distributional states.
To not cut too much to the coffee break, I'm sorry. If you have any extra questions, okay, fine, one, and then coffee break. I hope it's brief.
Okay, the question is that you took this point of view of adding a little loop instead of adding a bigger loop, and it's just a bigger loop as if you had a triangulation of given by the spin network or something, and then adding a bigger thing that doesn't change the graph. Just I asked this thing as a route to connect it to spinform models and the deformation algebra there. Do you have any comment on that?
Yeah, so this is, okay, probably the question is short, but the answer may be a little long. You can cut me off. This really has to do with understanding the physical state space. And there is, so contrary to sort of what people thought, right? The physical state space, in order to actually get non-trivial solutions, is an extremely complicated affair, right? And when you actually solve physical states, these are linear combinations of these spin network states, right? And in this, so you will certainly have things where you add these small loops, but you also have objects which somehow which have to be there, which are more analogous to having these larger loops, right? And I can tell you more about this in detail. This is related to this propagation work which I did with Thomas. So there is room, actually, I think, for at least some amount of contact with this, but maybe not in exactly the way you want, but we can talk about it more.
Great, indeed. Let's continue the conversations over the coffee break. One big thank you again. So this coffee break is still at the usual place in the Cultuurcafé. The coffee break this afternoon will be in the hallways, just so you're aware. Enjoy. 11 sharp. Per usual, move to the insides. That would be great for the people that arrive a little bit later. I think, yeah, let's just get started. So next up, we have the string/holography session, and we have someone all the way from the other side of the Netherlands. So very, very far. I guess for U.S. standards, he would, or Indian standards, or China standards, or wherever, he would be considered our neighbor. I guess, yeah. So let me introduce our neighbor, Jan de Boer. He will kick us off this session, and he also has the challenge to review lots of things and show the latest work. So I'm sure it will be interesting. The floor is all yours.
Thanks. Yeah, so thanks a lot for the invitation to speak. It's a bit of a daunting challenge, I found, to give an overview of this particular subject in 1 hour and combine it with some recent insights, but we'll see how it goes. I also try to think a little bit about various and I also see that presumably I should have referred to many other talks in this talk, but yesterday and the day before I gravity in terms of maybe a local quantum system in one dimension less, because as far as entropy and information goes, those things scale in the same way. And that's a very interesting sort of reduction of the degrees of freedom. And it's not obvious, because if you take maybe a gas of gravitons, that would still have an entropy that scales with the volume. So it's very much something that has to do with high energies and trying to compress information and energy together. This is just sort of saying the same thing. So this holographic principle, again, it's a philosophy that was pioneered by Het Hoofd and Susskind. It's the idea that it should be possible to repackage all the information of, say, a 3D gravitational system on some two-dimensional screen, where on the two-dimensional screen, if that would be a local system, then as far as entropy and information goes, there should not be any loss of information. So just from counting information and entropy, it should be possible to store all the information of a gravitational system in terms of a local system of one dimension less. This hypothetical auxiliary system that has local degrees of freedom live on some codimension 1 surface called the holographic screen. And exactly what this holographic screen is and where you should put it is very unclear. This was just some very like a high-level argument that this should maybe in principle be possible, and you can refine this argument somewhat, but it doesn't really tell you exactly where to put the holographic screen, what lives on the screen, what happens when things go through the holographic screen, must the screen be time-like, would you put it anywhere, etc., etc. So there are many questions that are not so clear if you want to actually technically implement the holographic principle in a precise way. Now there's one situation where we can actually implement it in a precise way, and this is the so-called ADS-CFT correspondence. There's many ways to explain roughly what it is, but I always like this cartoon. So the ADS-CFT correspondence, so let's first talk about ADS. So ADS is anti-de Sitter space. It's a solution of the Einstein equations with a negative cosmological constant. And you can think of it as this negative cosmological constant as basically putting gravity in a box. You can think, loosely speaking, of this negative cosmological constant as sort of putting a potential well in your system. And one of the nice things that this particular geometry does is that quantum fluctuations, which in the middle of the well can be arbitrarily large, they die out as you go towards the boundary of the box, towards the boundary of the space-time. And because quantum fluctuations die out as you go towards the boundary of the space-time, if you go all the way to the boundary, there's no quantum fluctuation anymore. And that means that at the boundary of this box, space and time are in fact well defined, because the metric on the boundary does not fluctuate as a consequence of having this particular geometry and a particular choice of boundary condition. So that means that in some sense, we now have something to hold on to. There is this boundary that doesn't fluctuate. One of the main problems, as I'm sure you all know, is if you have a quantum gravitational theory, there isn't really much to hold on to. All observables are at best relational. You cannot unambiguously define the point or anything. There's just not much to hold on to if your manifold fluctuates wildly. But if you put the system in this particular box, then on the boundary, there is something very precise to hold on to. There's a well-defined notion of time and space on the boundary. And this is what the geometry looks like. It is very simple. There's a radial coordinate, which is sort of the direction along the potential. There's just some Minkowski space-time or something else that you can put here, and then there's just some exponential factor there. And this exponential factor is essentially what gives rise to this sort of effective potential well in which your gravitational theory lives. This is the Wikipedia version of that geometry. It shows you that in this picture, every sort of colored triangle is supposed to have the same area, and this picture is merely illustrating the fact that as you go towards the boundary, space and time stretch by this exponential warping factor. Now, since we now have a codimension 1 surface, which is the boundary of this box, and moreover, time and space on this boundary are well defined, you could think that perhaps this boundary is the perfect place for the holographic screen to live, because it has a well-defined time and space. In particular, it could support a local field theory with no gravitational degrees of freedom, because time and space do not fluctuate. So we could imagine that there is this holographic screen for this particular case actually lives on the boundary of ADS. And it has one good feature of that, is that we have lost the dimension. It lives on the boundary. So it's precisely in the spirit of what we wanted from the holographic principle. And the other interesting feature is that because we have a box with a boundary, effectively a boundary, it's technically a conformal boundary, but that's not so important for most things that I say, is that the Hamiltonian constraint of general relativity, we know it's equal to, it basically tells us that the Hamiltonian is 0. However, there are also boundary terms. And therefore, the Hamiltonian inside the box is essentially 0. However, it does have boundary terms. And therefore, you could imagine that all the dynamics of the theory effectively lives on the boundary, just from this simple canonical gravity argument. Now, you can do semi-classical physics in this box. So we simply take gravity, we can add some matter fields, we can look at fluctuations of those degrees of freedom. And by just doing semi-classics, you can derive, based on the hypothesis that there is some system living on the boundary, that there is this holographic screen at the boundary, just based on purely semi-classical reasoning, you can derive many different features of that hypothetical thing that lives on the boundary. So everything that's written here simply follows from semi-classical reasoning. You don't need any UV completion of gravity or anything like that. All of these properties follow from semi-classical reasoning. So then you can ask, well, okay, that's nice. So these are all semi-classical building blocks of this thing that lives on the boundary. Do we actually have concrete examples? And this is where string theory comes in, because in the context of string theory, it is possible to derive concrete examples of this ADS-CFT correspondence, where you have a particular gravitational theory in ADS. It is not a general theory, it's a specific list of possible theories. And for each of those, we know precisely the thing that lives on the boundary. So up to here, everything was sort of semi-classical. But if you want to go beyond a semi-classical analysis and want to have a very precise statement where you say that a gravitational theory in ADS is exactly the same as some local system that lives on the holographic screen, then yeah, you can shop for one of those examples that string theory produced. And there's many of those. I should say that none of those include pure gravity in ADS. All those examples have the gravitational degrees of freedom in ADS and infinite towers of massive fields as well. And there is no known example where this is a purely gravitational theory. And from this point of view, it remains unclear whether there is a UV completion of gravity in ADS that does not require the addition of lots and lots of additional degrees of freedom. An interesting feature of these conformal or quantum field theories that live on the screen is that they're local and unitary and strongly coupled, and the prototype example is a large N gauge theory, where the N refers to the rank of the gauge group, like a large N limit, say of SUN Yang-Mills theory. And also most of these examples are supersymmetric. But those are some details that are not important for the remainder. Now, this was very specific for ADS, because it has to do with the way we set up the boundary conditions in ADS and the way quantum fluctuations die out near the boundary. And you could ask, what about flat space and other geometries? Well, as far as flat space goes, if you go back to this picture here, you can sort of think as this potential well, if you wish, as some sort of large volume regulator of flat space. And if you go somewhere in the middle here, and you go to distances that are much shorter than the length scale that is set by the negative cosmological constant, then on those distances, this system will behave effectively like flat space. So you can think of this box as being some sort of regulator of flat space physics. But we currently don't know, for example, how to put like a piece of cosmology in this box. So you could imagine that if you could put some cosmology in the middle of this box, we could also use the same holographic screen to study cosmology. That is it's currently unclear how to do that in any precise way. You could also ask, what is special about this boundary? Why can I not take any gravitational system and just put some boundary somewhere and declare that maybe this is my candidate holographic screen? Well, I think one important issue is that you can put boundaries somewhere. You can take a gravitational system and truncate it somewhere and just declare that you have like a Dirichlet boundary condition somewhere. But if you do that, it's not clear that on that screen you will get anything local. Because in most cases, the light cone on your screen will be misaligned with the light cone of the gravitational theory. And if that happens, then there's no way to imagine anything local to appear on this boundary. And it could just be some random non-local whatever that we have no technical control over. Now, because we have this boundary, which is well-defined, we also have well-defined, non-perturbatively well-defined observables, because you can put operators on this boundary, and you can compute correlators on this holographic screen. And so ADS-C, it's an equivalence. The statement is that a quantum gravitational theory in ADS is identical to a quantum field theory on this holographic screen. They're the same thing. They're two different descriptions of exactly the same thing. They're two equal descriptions. Now you can ask, for example, so whenever you do a computation intrinsically on this screen, which has some quantum field theory living on it, any intrinsic computation there, you can ask what is the corresponding computation that I should do in the gravitational picture. Right? There's two equivalent descriptions. You can do a computation purely in the screen, and you can do a gravitational computation. And those two things should be the same, if this statement is true. Now, for example, if you want to compute a correlation function of, say, 4 operators that live on 4 points on this holographic screen, so this circle here represents the screen at the boundary of ADS, then you can do, in principle, you can do some 4-point correlation function computation in the gauge theory, to get some answer, and then you can ask what's the corresponding computation on the gravitational side. And on the gravitational side, it basically boils down to a bunch of Feynman diagrams, except that these are Feynman diagrams in real space, not in momentum space. So perturbative Feynman diagrams, so this is in some sense a very conventional perturbative gravitational computation with some vertices and propagators. And just doing this coordinate space Feynman diagram agrees with this correlation function computed intrinsically in this boundary theory. From this point of view, the only well-defined observables that you have are local operators that live on the screen. Because the screen is the same as the quantum gravitational theory, and we know what the right observables in a quantum field theory are, the algebra of local operators, if you wish. So those are the only well-defined, non-perturbative, well-defined operators in the theory. So the only precise computations that you can do is put a bunch of operators on the boundary and compute correlation functions. That resums diagrams of this type. So the only way you sort of get access to the interior is in an indirect way. You never do a precise local computation anywhere. Maybe that's precisely what you want in a quantum gravitational theory. The only thing that you can sort of see is these indirect effects of these diagrams. And then you have to do some version of inverse image reconstruction. I always compare it to like medical imaging, where you shoot things through your leg. You cannot look directly in your leg, but from the things that you shoot through, you can reconstruct what is going on inside your leg. Another example that we'll come back shortly to is you can also look at the finite temperature partition function of the theory that lives on the boundary or on your screen. And if you want to compute a finite temperature partition function in a quantum system, then typically what you do is you take the time direction, you make it imaginary, and you make it periodic with period inverse temperature. And that is how you define, and that path integral in the quantum field theory computes for you the finite temperature partition function. You can ask, what is the corresponding gravitational computation? The corresponding gravitational computation then requires you to find a gravitational solution of the gravitational field equations with this particular boundary condition. Because you can, once you set up this correspondence between the quantum field theory and the gravitational theory, you can also change the background on which the quantum field theory lives. And then the question you have to answer is you have to find a solution of the field equations with this new boundary condition. In this case, for sufficiently high temperature, the standard solution looks very much like a Euclidean black hole solution. Many of you may know that if you Wick rotate a Schwarzschild solution, the effective geometry looks like a cigar, where the Euclidean time circle smoothly pinches off near the horizon of the black hole. Something similar happens here. And now you can relate the on-shell action. So you have a solution of the gravitational field equations, a classical solution. That's in a saddle point approximation the leading order contribution to this gravitational computation. There would also be one loop determinants and maybe non-perturbative stuff. But the statement is that to leading order, therefore, the finite temperature partition function of the theory is equal to the classical gravitational action evaluated on this cigar geometry. This is a classical computation. This is in principle a very difficult computation because these quantum field theories that live on these screens, they are in general very complicated, strongly coupled theories. And you cannot use perturbation theory to compute their finite temperature partition functions. So this is an example where an incredibly difficult computation in the field theory is mapped to a very simple computation on the gravitational side. So one application of this ADS-CFT correspondence has not been necessarily to solve deep problems in quantum gravity, but a very other important application is that it allows you to do very difficult computations in the field theory, in strongly coupled field theories, using gravitational methods. It's even been suggested that with setups of this type, that if you engineer the right quantum field theory here, that perhaps you could find a gravitational interpretation of high TC superconductivity. So here are a few conceptual observations that maybe try to connect a little bit to some other things that have been said in this meeting so far. One of these is that there was this issue of time. Well, in this particular case, time on the boundary is well defined. Time in the interior is at best approximately defined. And you can elaborate on all these statements in a technical way. Another thing that happens here is that the ground state of the theory in ADS, which is the same as the ground state of the whole theory on the screen, you can prepare those with a no-boundary Euclidean path integral. So in this particular case, if you wish, the no-boundary proposal works well. It just spits out the ground state and there are no weird subtleties. Nor do there seem to be any particular issues related to the indefinite sign of the Euclidean action. You can just compute the Euclidean action, do a one-loop computation with some Wick rotation, check that that is the right answer from the field theory point of view, etc. It's also interesting to notice that this extra dimension that goes in the box, it's related to sort of scales in the problem. So this extra dimension is a geometrization of scale transformations. This is a very contentious statement because to precisely argue whether this is true or not, you need a precise definition of emergence, which I always happily leave to philosophers. But some people have claimed that this is a nice example of emergent spacetime. And it's also interesting to see whether something interesting happens if you go to very high energies. This quantum system on the boundary is UV complete. And because it's UV complete, we can in principle go to very high energies. And you can ask whether something special is happening if you go to very high energies from the boundary point of view, where in principle you have precise control. For example, you could ask, maybe in the spirit of asymptotic safety, whether there is an interesting UV fixed point somehow emerging in this context. That's actually not entirely obvious, because on the boundary we have some conformally invariant quantum field theory, and if you go to very high energies, it still is the same conformally invariant quantum field theory, and it doesn't really run towards a particular fixed point. maybe you could argue that if you start with a quantum field theory on a compact manifold, that it decompactifies the compact manifold, and that is sort of your UV fixed point. But much more than that doesn't seem to be happening in this particular case. I wanted to briefly mention the role that quantum information plays in all of this. Because for some obscure reason, quantum information seems to play an important role. I'm not exactly sure why, but maybe it has something to do with the fact that, say, black holes, they behave like thermodynamic objects. To describe thermodynamic objects, we use methods of thermodynamics and quantities like entropy. And entropy is one way to quantify information. Quantum information is another way to quantify information. And maybe because somehow gravity is intrinsically thermodynamic in a funny way, this is maybe the reason that I don't have a better answer why quantum information is so important in quantum gravity somehow. So to quickly, I just want to very quickly mention that. So there is something that is called entanglement entropy. What is entanglement entropy? Well, if you have, say, an EPR pair or a Bell pair of two entangled qubits, and this is the prototype example, then this is an entangled state. And entanglement is the thing that makes quantum physics different from classical physics. Because thanks to entanglement, you can have a situation where the outcomes of measurements in causally disconnected regions can be correlated. Because if you have this state and you separate the two qubits over 1 million light years and you simultaneously measure those qubits, you know that the outcomes will always be equal. So outcomes are correlated, and in a classical situation this would never happen.
Why not? It's simple to construct probability distributions that have a correlation that has no causal connection. We see them in the universe actually.
You want to take that now or leave it till the end? That's okay.
I'll leave that to the end because with almost every sentence I say we could have discussions about the precise terminology. In any case, if you have a quantum system, I'm happy to discuss it later by the way, but if you have any quantum system that lives in a tensor product of two Hilbert spaces, there exists something that is called entanglement entropy, which is a quantitative measure for, roughly speaking, the number of such entangled Bell pairs that are shared between A and B. So it is a quantitative number that tells you how much entanglement there is between A and B. If the number is 0, then A and B, then the state is in a tensor product. And that means that there is no entanglement between them at all. Now what's interesting is that in this ADS-CFT context, quantum information is geometrized as follows. So here is your holographic screen on the boundary. There is a local quantum field theory living here. In this local quantum field theory, we can separate basically the screen in two regions, B and A, which is the complement of B. Because it's a local quantum field theory, the Hilbert space of the local quantum field theory factorizes in degrees of freedom in A and degrees of freedom in B. And then you can ask how much entanglement is there in the ground state of the quantum field theory between A and B. And in any quantum field theory, even the ground state is highly entangled. So there's a lot of entanglement in this quantum field theory between A and B. You can ask how much is it? Can you quantify how much entanglement there is? Now that's a very difficult quantum field theory question. If you actually want to do this computation in a quantum field theory, it's very complicated. And it has only been done basically in a few simple free field theories. And even there it's complicated. But for these special quantum field theories that live on the holographic screen, the amount of entanglement between A and B can also be computed using the gravitational description. And in the gravitational description, what you simply need to do is you need to take the boundary that separates A and B, and you need to find, you need to find a minimal surface, so a surface with the smallest possible area that connects to the boundary that separates A and B. and then the entanglement entropy between A and B is simply given by the area of that minimal surface divided by 4G. And it's remarkable that this equation has exactly the same form as the Bekenstein-Hawking entropy formula, although in this case there is no horizon to be found anywhere. It is just some codimension 2 spatial surface that lives in this geometry. This has maybe led to some, this connects maybe to old ideas that maybe black hole entropy is a version of entanglement entropy, maybe they're the same and so on. That's not what's going on here, but it's nice to see here that a very complicated computation can be related again to a very simple computation. But more importantly, there is like a geometrization of information going on. And that seems to be a more general feature, because there's a whole literature in quantum information theoretic concepts. A laundry list is given here, there's many more. And many of those can in fact be connected to various notions of quantum gravity. And maybe ultimately we should try to reformulate quantum gravity purely in information theoretic terms. But that has not been achieved yet. So some bits and pieces have been formulated in this language. But for the rest, yeah, we don't know yet. There's a lot of loose ends here. This is just a summary, which I'll skip. Now I want to move on to black holes in ADS. So what happens if you put a black hole in ADS, and what can we learn about that? Now a black hole in ADS, by just studying those things, you can see that a black hole in ADS is described. What is the description in terms of the quantum theory? Well, the quantum theory turns out to just be at finite temperature. So a finite temperature quantum field theory is gravitationally described by a black hole, at least if the temperature is high enough. Black holes in ADS are a bit different from black holes in flat space, because a black hole in ADS, if it Hawking radiates, the Hawking radiation gets reflected off the boundary and goes back into the black hole. And that is why a black hole will reach thermal equilibrium and not fully evaporate. So black holes in ADS have a positive specific heat, whereas black holes in flat space have a negative specific heat. That's why they correspond to sort of a conventional finite temperature state in the field theory. These also have positive specific heat. So here's a nice little test that sort of illustrates some of the universal robust features of ADS CFT, if you wish. So if you go to ADS 3, which is a three-dimensional gravitational theory, it's a bit of a weird theory because it's in 3 dimensions, so it does not have local degrees of freedom. Nevertheless, you can write down a black hole solution in ADS 3, which is the so-called Bagnados-Teitelbaum-Zanelli black hole, the well-known black hole solution, and it's given here. This describes a rotating massive black hole in 3 dimensions. And you can compute the Bekenstein-Hawking entropy. In this case, the horizon is just a circle because we're in 3 dimensions. And you just compute the horizon area, so that's 2 pi r plus divided by 4g, so that's pi r plus over 2g. And if you express it in terms of the mass and angular momentum of this solution, I did not give you the relation between the mass and the angular momentum, and r plus and r minus. But if you use the relation between m and j and r plus and r minus, you get this equation for the Bekenstein-Hawking entropy. Now, ADS CFT would suggest that there is a holographic screen in 2 dimensions, and that perhaps generically these theories are dual to 2-dimensional conformal field theories. So if ADS CFT is true, then this entropy formula should be reproducible by looking at the entropy of a 2-dimensional conformal field theory at high temperature. Now, 2-dimensional conformal field theories are very special because the entropy at high temperature is independent of the details of the theory. There's only one parameter in a 2-dimensional conformal field theory that is relevant in finding the entropy at high temperature, and that is the so-called central charge of the 2-dimensional conformal field theory. Like a free boson has central charge 1 and 20 free bosons have central charge 20, etc. So there's only one such a parameter, the central charge, and there's a universal formula for the high temperature density of states in any two-dimensional conformal field theory, where the only sort of free parameter is C, and L0 and L0 bar are two quantum numbers. They're basically related to the mass and angular momentum. Now you can do the translation, and without going into the details how the numbers work, you can already see that these equations look very similar to each other. And if you work out how C and L0 and L0 bar are supposed to map to G and M and J, then you can check that this equation is identical to that equation. So somehow, I think this is a very nice sort of consistency check of ADS-CFT. And it's important that this equation only holds if you have a local, unitary, modular, invariant, two-dimensional conformal field theory. Otherwise, this equation does not hold. And all known conformal field theories have lots and lots of degrees of freedom, certainly at high energies. I think the precise equivalence between these two equations strongly suggests that if you want to UV complete any 3D gravitational theory, the UV completion, at least in ADS3, presumably is a 2D CFT, and that automatically, again, requires an additional tower of massive states, because we have no examples of CFTs that have no massive states in them whatsoever, and just have sort of the thing that corresponds to the graviton. Now, there's many things that you can study. I wanted to highlight these two little red things, because if you study a black hole in ADS, then you will discover it's a very extreme object. It's a very extreme object in many ways, because if you throw something into a black hole, you have a black hole in ADS and you throw something in it, that thing will perturb the black hole, it will slosh back and forth for a while, and then it will settle into a new equilibrium situation. If you translate that into the boundary theory, in the field theory language, what you have is a field theory at finite temperature. But there, just as like with water and so on, if you perturb that theory locally, that perturbation will dissipate through the system, and the system will reach the thermal equilibrium again. It looks like dissipation. And you can study all these processes and discover that they basically go as fast as humanly possible. So black holes are the optimally designed objects as far as thermalization goes. They thermalize very fast. And another way to see that they're very extreme objects is by studying chaos near a black hole, which technically you can roughly do as follows. So classically, chaos is the statement that if you have two trajectories in phase space, and you start with some initial condition and you evolve in time, that these two trajectories will exponentially diverge. And the exponent that appears is called the Lyapunov exponent. It's one of the classical diagnostics of chaos. If you translate this type of computation through this, that, and that argument, you can see that in quantum mechanics the closest cousin of this is something like a commutator squared. If you, and this gives rise to the study of so-called out-of-time ordered correlators, which are the quantum version of classical chaos. And they can also diagnose a quantum version of a Lyapunov exponent. And you can compute this Lyapunov exponent for the case of a black hole, and you find that this Lyapunov exponent is 2 pi over the inverse temperature. Moreover, there's a general argument with some assumptions that this Lyapunov exponent in a large number of quantum systems cannot be any larger than this. And that means that black holes are also the most chaotic quantum objects in nature. There's nothing that can be both quantum and more chaotic than a black hole. So there's, in some sense, it's interesting that black holes, they saturate all kinds of bounds. So they really are the most extreme thing that you can possibly imagine. Now, one of the things that is annoying is that if you have a black hole and you perturb it, for example, you have an infalling observer, and you want to know what happens at very late times. Because this system thermalizes so fast, there is a particular time scale, which is called the scrambling time, after which a low energy observer sees nothing anymore. You throw something in the black hole, and after a certain amount of time, it just looks like a black hole again. And the energies required to see something happening will become exponentially large. So after some critical time, which is sometimes called the scrambling time, you sort of, as a low energy observer, you don't see anything interesting anymore. So if you only do low energy measurements, you will never be able to see what's going on. And you can ask whether there are other non-observables, maybe theoretical quantities, that allow you to track some interesting feature even after a system has thermalized. And one interesting quantity that has gained some attention recently is something called complexity. And that's a notion that's coming from quantum computation. It looks like a complicated equation, but it's super simple. So suppose you have an initial state psi 0, a final state psi, and suppose you have a quantum computer, which means that you have a set of unitaries that you can apply. So a quantum computer is nothing but applying a sequence of unitary operations to an input state. So this is sort of the number, this is like your programming language, and also we should, to be precise, define some margin of error epsilon. Then the complexity of a state psi is defined as the length of the shortest computer program, quantum computer program, that maps the initial state to the desired output state up to an order epsilon. And this is a very useful notion, and it tells you, for example, how difficult it is to do certain quantum computations. And this is a notion that has been studied much and is studied much in quantum computation circles. Now, even after a system thermalizes, you can do examples of that. You can see that complexity keeps on growing, even after a system thermalizes. And that really is very suggestive. Let me skip that one. That maybe complexity is a useful notion. Maybe it's a theoretical notion, but it's possibly a useful notion to study black holes at late times. After they have completely thermalized, perturbations have disappeared, and so on. And this has led to a series of conjectures, in particular complexity equals volume. Because if you write like a two-sided, say, Schwarzschild or ADS black hole, and you follow it at late times, the volume of a spatial Cauchy slice also increases for a very, very long time. The problem is that there is no precise conjecture. This is a bit vague. The other problem is that we have no precise field theoretic definition of complexity, which is supposed to be relevant for these particular cases. So this is, in spirit, this seems to be a correct thing to think. And it's well possible that there is a precise notion of complexity that still needs to be found that sort of relates you to volume, but this has not been found yet. So, just to emphasize a few things, so these strongly coupled theories that live on the holographic screen, their spectrum roughly looks like this. There is a very sparse spectrum of low-lying states. All low-energy observers and all the matter fields and so, they all live in this low-lying part of the spectrum. And then there's roughly a transition to a high-energy part of the spectrum where the spectrum becomes very dense, it becomes chaotic. Here the spectrum is roughly integral. Here it becomes very chaotic, extremely chaotic, and very dense. And black holes live here, and our observations live here. Now, I will not explain in detail, for lack of time, these three puzzles, but I want to say maybe a little bit about the first one and then maybe skip the second and the third one, and you can ask me later. The first one is the puzzle of Euclidean wormholes, because in ADS-CFT we have a gravitational theory. It has one boundary. But if you take two holographic screens, and you have a field theory on one screen and a field theory on the other screen, and you ask, are those two screens correlated with each other? Then the answer naively appears yes, because you can have these so-called Euclidean wormhole solutions that have two screens as their boundary rather than one screen. But in ADS-CFT we always have one boundary, and there's just a single theory there, and all the string examples that we know have a single theory living on the screen. So what does it mean to have correlations between screens? It looks like these two screens are no longer independent. Now, Stated differently, suppose that you want to put the first screen at temperature beta 1 and the other screen at inverse temperature beta 2, and you want to compute the expectation value, then naively it looks like there is a difference between the connected and the disconnected expectation value of these finite temperature partition functions. Because the connected one has these disconnected geometries and this Euclidean wormhole, whereas the disconnected one only has this. And that leads to this weird observation that the connected, or the two-point function of two partition functions of two different screens, is not the same as the product of the partition functions of the individual screens. However, these partition functions, they're supposed to be numbered. This is supposed to be a number. And if these are numbers, then the expectation value of 3 times 5 is really the expectation value of 3 times that of 5. This cannot happen if these are numbers. So then you can ask, what the hell is going on? Now, if there were hidden superselection sectors, and I think on Monday Arthur Hebecker referred to this possibility, if there's hidden parameters somehow, that might be related to baby universes or some other fun stuff, then this equality no longer needs to happen. So if there is hidden parameters, hidden variables floating around, and this does not happen. And this has led to the question, or whether gravity at some fundamental level involves averaging over parameters of some sort. Well, but there is a different perspective, which will give something somewhat reminiscent of this, but the interpretation of these alphas is different. And that has to do with a different point of view, which is take a statistical perspective on semi-classical gravity. So if you have a gravitational theory, from a particle physics point of view, we always believe this to be a low energy effective field theory, which is valid up to some energy scale, but not above that energy scale. That means that there is some fundamental uncertainty about the theory. Moreover, we just probe it with low energy probes. And if we want to model an unknown system based on incomplete information, then precisely the method of statistical physics apply. And this was, for example, already applied by Wigner in the 50s when he tried to model features of the spectra of heavy nuclei with random matrix theory. In this particular case, it can be implemented somewhat technically by making the following statement. Suppose that semi-classical gravity, so that's not the UV complete microscopic description, it's essentially only the things that low energy observers can see. You could say, well, this is not dual to a single theory, it is dual to an average over theories, where all those theories have the property that as far as low energy observations go, they should be indistinguishable from each other. Because from a low energy point of view, we would not know which of those H's it is. And if this is the right description of semi-classical gravity, then if you now do this measure, so now this measure plays the role of these alpha parameters, then this 2-point function is no longer equal to the product of the 1-point functions. And you can do, this sounds maybe like it's impossible to test, but in fact you can test this in some detail, and it turns out to work. And if this picture is correct, there are actually two predictions, namely first of all that there's no new information in these Euclidean wormholes, and the second one is that they should disappear once you go to a UV complete description. Because if you have a UV complete description, there's just a single H, you don't have an integral, and that means that this measure becomes localized on one Hamiltonian, and then this whole thing will disappear. So there's a lot of evidence that you can collect for that. I've worked quite a bit on that over the last few years, and that seems to work fine. Then there is a interesting story about the information paradox, which maybe we can leave for a different discussion, but from my personal perspective, the information paradox has essentially been solved, at least in the ADS context. And the third thing is I want to say something about the infalling observer, which I think has also seen interesting progress, which I will also skip. Just mention that this notion of complexity seems key if you want to make a very precise statement about infalling observers. And the last little thing I wanted to mention is, to continue on this wormhole story, is a possible connection between 3D gravity and a discrete model. So I told you that semi-classical gravity could be interpreted, and it's consistent with wormhole computations, as an average over indistinguishable theories. Now, if you take a two-dimensional conformal field theory, so let's now apply this to a three-dimensional case. So we take ADS3, we apply this to that case. Now, then we want to figure out what the indistinguishable two-dimensional theories are. Two-dimensional theories are classified by a list of scaling dimensions and so-called structure coefficients, the operator product expansion coefficients, which have three indices. They basically tell you that it's a standard quantum field theory notion that if you bring two operators close together, they sort of fuse into a third operator. And these are the essential structure constants of that. And these things are not completely random. In order to have a proper two-dimensional conformal field theory, they have to satisfy a bunch of consistency conditions, the so-called Mohr-Seiberg axioms of two-dimensional conformal field theory. And one important one of those is if you have compute a 4-point correlator, you can use these CIJKs that tell you how things merge into a single operator. To do this computation in two different ways, you can first merge those two channels and those two channels together, or you can do it in this way. But consistency, one important consistency condition of a two-dimensional conformal field theory, or any conformal field theory, is the so-called crossing symmetry, which tells you that this should be equal to that. Now, if you apply that to this set of two-dimensional conformal field theory data, and we focus a bit on this CIJK, these OPE coefficients, then we can write a probability distribution on theories that are indistinguishable from a low energy point of view. And it will look basically like an exponent of minus a large number times the sum of the axioms squared. Because in the limit where A goes to infinity, this would enforce all the axioms and you will get a two-dimensional conformal field theory. But if A is large and finite, then all these things are still indistinguishable from a low energy point of view. And now if you grind away and you plug this all in, it turns out that you get a fourth order matrix model or tensor model for those structure constant CIJK. And the fourth order vertex that you get is given by some tetrahedron that we also saw this morning. Interestingly, the weight that is associated to this tetrahedron is given by a Wigner 6J symbol. It's just not a 6J symbol of SU2 or the Lorentz group, it's a 6J symbol of the Virasoro algebra. But that is part of the intrinsic symmetry of these particular theories. So it's interesting that this is actually very reminiscent of all these old discrete approaches, like Radboud is also it's closest in spirit to something that Bulatov did, although he used 6J symbols of SU2 and quantum deformations of SU2. And here we get his Virasoro 6J symbol. But it has many features that are reminiscent of quantum groups. And it also seems to be related to some other approaches that have to do with so-called Teichmüller TQFT. So it's certainly interesting that just by following this sort of statistical approach to gravity, we seem to be making a connection to certain discrete approaches. And maybe this is a nice bridge to explore further. Then in the last 2 minutes, I'll just click through a few slides with some things. So these are 8 questions with sub-questions. So the first thing that would be nice to clarify is what is the role of quantum information precisely? I don't know exactly what it is. But as I said, maybe gravity is nothing more than a geometrization of quantum information. The second thing is the role of quantum computation. More and more, we seem to be seeing that computational complexity is of fundamental importance in quantum gravity. And it will be interesting to understand why and how far that relationship goes. The third thing that's also important is that gravity is a non-local theory. You could already see it's a non-local theory by this holographic approach to begin with, because if it were a local theory, the entropy would scale with volume and not with area. So it is a non-local theory. Now those non-localities don't bother us too much, but they are very important if you look at black holes. And they're also the key at the end to resolve the information paradox. So in one sentence, the information paradox is resolved by allowing exponentially small non-localities on all length scales in your theory that have zero impact on low energy observations, but that are precisely enough to sort of get the information out, but not in a way that any low energy observer would ever see. There's also the question of the role of the observer. So very often we ask meta-observer questions about these systems. So we imagine that we have our ADS here and that we can manipulate it and so on. That's not very realistic. We are obviously always intrinsically part ourselves of the quantum gravitational system that we live in. And again, some recent developments suggest that maybe we should put more emphasis on this aspect of quantum gravity, a more observer-centric approach perhaps. In particular, there were some interesting developments in the context of algebraic quantum field theory, where adding an observer seemed to be an important ingredient. Then we would like to not just do ADS, but also like to do flat space and other spaces. So in flat space, there is an approach to holography in flat space, which goes under the name of celestial holography. There the holographic screen is essentially put at null infinity. But that's a bit of a weird screen. First of all, it's not clear that you have a proper local theory there. Secondly, it's not clear that the theory should be unitary, because things can go through that screen. And the third thing is it involves a null direction, so it's certainly not a bona fide standard local quantum field theory. But there has been quite a bit of progress. Certainly perturbative gravity can be reformulated in quantities that live on that screen. But so far there's no theory living on the screen. It is just a reformulation of the S matrix in flat space and a reinterpretation in terms of data and symmetries on the screen. And in cosmology, there's kind of a similar thing. If you're in de Sitter space, the reasonable place kind of to put the holographic screen is at future infinity. But that's a space-like slice, so that certainly does not carry a local quantum field theory that is Lorentzian. So there's many questions that are related still to quantum gravity in the Sitter space. We have seen that black holes are super chaotic objects. So it's incredibly difficult if you have a very chaotic thermodynamic system. It's very difficult to identify the individual degrees of freedom. Because if you let some system evolve in time, even for a short amount of time, things will be very chaotic. You will immediately spread out over phase space, and you always end up in a typical state, which is indistinguishable from other typical states. So you will always end up basically with an effective thermodynamic description, and therefore it's super hard to see the individual degrees of freedom. It would be nice to see them, because then you could say, the black hole consists of these 10 to the 180 degrees of freedom, but they're very hard to see. So in some sense, if you take all these lessons very seriously, it seems very hard to find observational consequences of quantum gravity for black hole physics. And the last one is this one, and I'll stop here. Thank you.
Thank you very much. I already see a few hands. We'll do this one first, and we'll go up next there. Yes.
Thank you for a wonderful review. I learned a lot. I was just wondering if you could post your slides somewhere so we could read the missing information that you coarse grain, which are equally valuable. And then I have a question for you. The ADS-CFT, of course, is a very powerful, beautiful description. But so far, I see gravity in the bulk being classical, and then quantum field theory, conformal field theory being quantum. So what do you mean exactly? What do you mean by quantum gravity in this context? The second part is, how would you see quantum information taking over or describing whatever you want in your definition of quantum gravity? Thank you.
Thanks. Yeah, so the first question, the precise statement is that the quantum theory on the boundary is equal to the quantum gravitational theory. There's an equivalence of quantum theories. Now, very often, in practical situations, when we look at the gravitational side of things, we evaluate things in a sort of standard saddle point approximation like you do in path integrals and so on. But you can go beyond that. You can, for example, do loop corrections perturbatively in the gravitational theory and match those loop corrections to things computed in the field theory on the boundary. You can also, in some cases, see non-perturbative instanton-like corrections from the gravitational side from field theory computations. So the complete statement is that a non-perturbative UV complete gravitational theory with ADS boundary conditions is exactly equal to a quantum, to a conformal field theory on the boundary. And both, it's a quantum-quantum statement.
So if I understood what you just said, the so-called quantum gravity referring to the gravity in the bulk actually is like the quantum gravity that we usually do, like perturbative quantum gravity.
Yeah, for practical purposes here, we end up doing something perturbative, but the statement is non-perturbative in nature. So the field theory on the boundary is equal to a quantum gravitational system with a boundary condition, and we can, in principle, also try to do some approach the interior in a background independent way, but it's very hard to connect any of those computations to field theory computation.
So that's what you mean by quantum gravity, the combination of the bulk and the boundary, what goes on.
It's two different equivalent statements. So it's an equality sign. Quantum gravity in the bulk is equal to the quantum field theory on the boundary. It's the same thing.
So if I prefer to stay in the bulk, perturbative quantum gravity is what you really refer to. Is that right?
No, the statement is that the non-perturbative theory in the bulk is equal to the boundary theory.
Okay.
It's just very hard to do explicit computations non-perturbative.
Do you care about the second part of my question about quantum information? To what extent can it reproduce your quantum gravity?
Yeah, so far that has not been possible. So a few things, what you can sort of get from quantum information is something that is roughly the Einstein equations, but not much more than that at this moment, I would say. So some bits and pieces can be obtained, but not a full description. And how we would leverage that in something more quantum and more non-perturbative is not clear to me at this moment. Yeah.
So, a lot of beautiful results, and actually thanks for a really clear talk. But one would now know, at least I would like to know, which of these results are particular to the particular models, because they are very particular models, and which ones can really generalize. So a simple question would be, if you have on the boundary a non-abelian gauge theory with running couplings, could you reproduce the beta functions from the gravitational side? I mean, that's one of the most simple questions from a quantum field theory point of view. Is that possible, or is it actually the present status that you have essentially only finite theories that you can deal with?
Yeah, thanks. That's a great question. I think the majority of things that I explained are model agnostic to a large extent. So a large number of features of ADS-CFT don't rely on, just rely maybe implicitly on the fact that there exists a UV completion, but the details are very unimportant for many things that show up. For example, some of these information paradox computations that I didn't have time to show, they're basically semi-classical methods. They don't really rely on anything. They don't rely on the detailed ingredients of my quantum gravitational theory. They seem to, they just follow from some general semi-classical analysis. So actually, if you really look under the hood, you will find that the vast majority of things that one does actually only rely on semi-classical gravity and not on the details, the very specific details of the very specific ADS-CFT examples that we have. Yes, let me now go to the second part. So, yes, you can, as follows. So at least an example. So suppose you take a conformal field theory on the boundary, and now you add relevant perturbations, so that the theory starts to run. We know how to model this into the gravitational theory, because this means that you're changing the boundary conditions, and we have shown that you can relate the gravitational field equations to the Collins-Szymanczyk equations, including the beta functions and the running couplings.
Sorry, great discussion. But I'm sorry I have to cut you off because otherwise the next speaker will have no time and that would be a shame. Thanks again. Lots of interest, clearly. And then again, I would like to ask, especially the people in the front, to move a little bit to the middle because we're really not allowed to have anyone in the stairs or in the back. So please make some space for the people that are up there. Otherwise, you know, the firemen are going to get angry at us and fine us, and that would not be great. So please move a little bit to the middle, and people up there, feel free to come down. And there's also always room here in the front. Thank you, Danielle. And great. Then on to the next speaker. Another neighbor, quote unquote, but this time from the south. In the Netherlands, we always have, well, I guess like any neighboring country, right? You have jokes about the other neighboring country. So I think in Belgium, all the think that the Dutch are very frugal, to say it kindly, which I think is a fair description. But here in the Netherlands, we always make jokes about the Belgians not being, well, to put it kindly, very intelligent. But I think this is Thomas is a very nice example where this is a counter-example that this is clearly not the case. And I'm excited to hear what he's going to share with us.
Okay. Thanks for the very nice introduction. Thanks to the organizers for inviting me. So I'm going to talk about exactly solvable lower dimensional gravity models, and it will be roughly based on these two papers that have appeared in the last half year, and also on some earlier work. So let me start by giving an introduction to the topic. So in recent years, and mainly sparked by developments in the Sajdev-Yukitaev models, and the SYK models, lower dimensional exactly solvable gravitational models have been reinvestigated in a lot of detail. And by lower dimensions, I mean 1 + 1 dimensions. And in this talk, I will discuss 3 such interrelated 1 + 1 dimensional solvable gravitational models. And in particular, I will observe and unify the underlying structure of the gravitational amplitudes that I will show in terms of group theory, in terms of representation theory. So this is an approach that has been my main focus for several years now. And well, I've done this with several collaborators whose names I give here. So first, an outline of my talk, and in particular, the 3 gravitational models that I will discuss. The first model will be 2D JT gravity. The second will be related to SYK, the so-called double-scaled SYK model. And the third will be Liouville gravity, and I will end with some conclusions. So first, the first gravitational model is 2-dimensional Jacques-Teilbaum gravity, or JT gravity. So it's a specific dilaton gravity model. And, well, dilaton gravity models are 1 + 1 dimensional toy models of gravity. So I've written down the Lorentzian action for a generic dilaton gravity model here. So it has the dilaton field capital phi that's being directly coupled to the Ricci scalar R. And I have allowed for an arbitrary dilaton potential V of phi, and also a possible boundary term. Now, JT gravity is a specific to the dilaton gravity model where you pick a linear dilaton potential. So V of phi is 2 times phi in the units that I've chosen here. So this gives you this bulk action, and I've also added the Gibbons-Hawking boundary term here. Now, this particular version of JT gravity, it has a negative cosmological constant. It's -2 in the units that I've chosen, which means I'm studying an ADS version of the model because I will be interested in holography. And in particular, now I will show you the results. I will review the results of exact calculations one can do in this model on the thermal amplitudes. So I want to show you the results of a calculation that you can think of as trace e to the minus beta h, where h is the Hamiltonian associated to this model, with some possible operator insertions that I will show you in the next slide. And I want to show you these calculations as they have been computed from the Euclidean gravitational path integral. Now, well, as was beautifully summarized by Jan in the previous talk, in Euclidean gravity, a black hole geometry, it has a contractible thermal circle. It is this cigar or disk topology. So if you want to do something with black holes, we are led to studying the disk partition function. And this disk partition function has a boundary. It has a circular boundary that is holographic, and that is of length beta, which I want to interpret as the inverse temperature. And this calculation has been done exactly. So the exact gravitational path integral on the interior of this disk with these boundary conditions. So it's z of beta. I want to interpret this as a canonical partition function. And the answer after doing the calculation, and I've skipped all of the details on how to actually do this, so you just have to trust me that this is the answer at the level of the disk topology, It's an integral over some auxiliary variable k. There's a density of states k sinh 2 pi k, and then the Boltzmann factor e to the minus beta k squared, so k squared plays the role of the energy. And you should think of this as a quantum gravitational thermal partition function whose thermal saddle, it matches the classical or the semi-classical JT black hole relation of the mass versus the Hawking temperature, but it corrects this to small black holes where you cannot trust the saddle anymore. So this is the exact answer of a quantum gravitational calculation in this model. Now next to this disk partition function, I will also have need of the boundary two-point function, where we imagine inserting two local operators at the boundary of our disk, one of them at Euclidean time tau 1, the other at time tau 2, and they are labeled by a parameter h, which you can think of as a conformal weight of a 1D CFT living on this boundary, but the details of this don't matter here. But you can do this calculation again, exactly, and it has been done by many authors over the past few years, and this is the answer. So it has a very similar structure as the partition function on the previous slide. So there's two integrals over two of these k variables, k1 and k2, and we have the same density of states, we have it twice. And then we have these Boltzmann factors or Hamiltonian propagation factors, where tau is, let's say, tau 1 minus tau 2, and then beta minus tau is the complement on this boundary circle. And then you have these gamma functions, so when I write the plus minus sign, I will mean you have to take the product of all cases. So there's secretly a product of 4 gamma functions here, and this object is the thing that makes this integral complicated, and you cannot analytically compute it. You can do it numerically, but you cannot write down, or you cannot at least simplify this in an obvious way, generically. Now we can make an observation on these amplitudes, so both the disk partition function and the boundary two-point function, and that is that the building blocks that appear in these amplitudes, so the measure, the k squared here, and these gamma functions, they all have a nice group theoretic interpretation. So in particular, if you focus on the continuous series irreducible representations of the group SL2R, for which this J quantum number is minus a half plus I times a real number, and I call that real number K, and it's the same K that appears here, then, well, it's known that K squared is a quadratic Casimir up to this shift of 1/4 that I will ignore here. It's also known that this measure here, K sinh 2 pi K, is the Plancherel measure on this set of representations, up to some subtleties that I will omit for the purposes of this talk. And also these gamma functions that appear here, you can just mathematically write these as an integral over some auxiliary variable phi, and then a product of 3 objects that I colored in blue, black, and blue here. So a modified Bessel function and exponential here. And you can identify these as the square of a Clebsch-Gordon coefficient of the group, or a square of a 3J symbol. In particular, if you look at Wikipedia, for instance, the Clebsch-Gordon coefficient square can generally be written as a group integral of a product of 3 representation matrices, each of these depending just on one representation label, of course. And that's precisely the structure we have here. So we see the same type of structure appearing here as you would have in group theory. And in particular, then these modified Bessel functions that appear here, they should be identified as representation matrix elements of SL2R in the principal series representations, and these exponential functions here, e to 2h phi, as a discrete series representation matrix element. So these are just observations you can make when staring at these expressions. Of course, this is no coincidence to see SL2R structure in JT gravity, because it has been known since a long time, just a couple of years after Jacques van Teilbaum wrote down this model to begin with, that the first order formulation of JT gravity can be rewritten in terms of a BF topological gauge theory based on the SL2R algebraic structure. So this is the action for the 2D BF model. When applied to SL2R, you can show that this just matches the first order formulation of JT gravity. Now, this first line here was for a manifold that had no boundary. Now, I want to do holography, so I want to add a boundary. And if you study such a BF model on a manifold with a boundary, you can show that adding this boundary term and this boundary condition gives you a well-defined variational principle. And with this BF theory, with this boundary term, it's now relatively straightforward to discuss the Hilbert space of this model. And that's what I want to do here. So imagine we put this action in a path integral. The B field in the BF model, it just appears linearly in the bulk Lagrangian, so we can just path integrate over it. It's a Lagrange multiplier. It forces F to be 0, and if my topology is trivial, this means that A mu is G minus 1 d mu G for some group valued field G. At this point, the bulk term is gone, So we plug that in the boundary action, and we use that boundary condition that we have here. And you see immediately that the full dynamics reduces to just boundary dynamics of large would-be gauge degrees of freedom, just like you have in the 3D Chern-Simons-Wesson-Witten model story. So the full BF action reduces to this, which describes the dynamics of a non-relativistic particle moving on a curved manifold, which is the group manifold G. In our case, this will be SL2R. But this notation was for an arbitrary group. Now, the structure of this particle on the group manifold of this theory is very well known. It's easy to write it down. The Hilbert space is just L squared of G, which mathematically is fully determined by the Peter-Weil theorem, which states that L squared of G is spanned by all representation matrix elements. So we can write our Hilbert space as RAB, where R runs through all unitary irreducible representations of the group, and A and B are indices that run within each of these representations. In coordinate space, you just take the bra overlap with a coordinate group element, you just find the mathematical representation matrix elements. Now, these representation matrices that span our Hilbert space, RAB of G, you can physically or geometrically identify them as two boundary wave functions. So you can geometrically identify that first index A as corresponding to the left endpoint of an interval, and that second index B as corresponding to the right endpoint of this interval, as I showed you here. And moreover, these wave functions, they solve a time-independent Schrödinger equation. H RAB is CR times RAB, where H is our Hamiltonian of our particle on a group system, and CR is the quadratic Casimir in the irrep R. So these wave functions are energy eigenstates in this particular model. Now, gravitationally, our Hamiltonian is identified as a two-boundary gravitational Hamiltonian, so it evolves states defined on this interval upwards in this picture that I have here. And mathematically, the particle on a group Hamiltonian is just equal to the Laplacian on the group itself. So now I want to try to find an explicit expression of these representation matrices by diagonalizing the Hamiltonian explicitly. Now, mathematically, the Laplacian on the group manifold G is also the Casimir in the left or right regular representation of the associated algebra G. So I want to go through a little bit of math here, so bear with me. The left regular representation is on the group is defined in this way, so you just have a function of G0 and you act on the left with the group element G minus 1, so this forms a representation as you can easily show. Now let's look at the infinitesimal action here. So we just pick a one parameter subgroup and we take a small parameter epsilon, we take a derivative with respect to epsilon and set epsilon to 0. This defines the action of a vector field on that function that I call Li hat. And you can simplify this to this relation for Li hat acting on the group element is minus the generators times the group element, and very similarly for the right regular representation, which I haven't written down, but it's very analogous. So this is generically the definition. Let's now apply this to the case of JT gravity, so in the specific algebraic structure related to SL2R. So here I've written the three generators of SL2R and their commutation relations, so I call the generators E, F, and H. And then if we exponentiate, we can go from the Lie algebra to the Lie group. And in particular, I will use Gauss-Euler coordinates to parameterize a group element of SL2R, where I can write this element as a product of three exponentials, each of which just taking a single one of these generators. And I use the coordinates gamma, phi, and beta as coordinates parameterizing my SL2R group element. So I needed to choose very specific coordinates to write down a very explicit expression for these vector fields as first-order differential operators in these coordinates, as I will now show you. So for these specific coordinates, these are the three left and right regular vector fields, the algebra generators that one can derive very easily. And from these, you can go to the quadratic Casimir, which was the Hamiltonian as just a quadratic differential operator. And of course, this matches just to an expression that you find in math textbooks. The reason that I went through this exercise is because I will do it twice more for these two other related models. So this is the operator we want to diagonalize. Now, there is an extra feature here, and I will not go into the details here due to lack of time. But if we have holographic boundaries, such as we have in JT gravity, these indices A and B that parameterize our representation matrix element, they are not free indices, but they are fixed and constrained. In particular, one can show that this A is an eigenvalue of this, essentially the F parabolic generator, and B an eigenvalue of the E parabolic generator, so two of these three generators of SL2R. And this corresponds at the level of the representation theory that I'm showing you here to implementing the Brown-Hanot asymptotic ADS boundary conditions or the Hamiltonian reduction formulas if you're more familiar with that. So this is something you have to do. These are constraints you have to impose if we want to look at boundaries that are holographic boundaries. Now what this implies is in particular that, well, one of the left generators and one of the right generators are diagonalized, and I choose the eigenvalues to be -1 and 1. And it's very easy to see that if you restrict to eigenfunctions that satisfy these conditions, your eigenvalue problem just reduces to an ordinary differential equation. It's just a particle in exponential potential, which is diagonalized by these eigenfunctions, so this Bessel-K function. And this Bessel-K function was a thing that I had at the very beginning. These were these representation matrix elements that we identified that were hidden in the JT amplitudes. So here we find it as a solution of diagonalizing the Casimir eigenvalue equation, or the two-boundary Hamiltonian. Okay, so that was the first model. So now let's go to the second model, and we start completely, well, again, from zero, so forget everything that I said before. And this model comes from the SYK model. So very, very briefly, the SYK model is a quantum mechanical model in 0 + 1 dimensions of n Majorana fermions psi I that satisfy this Dirac algebra. And they have all-to-all random interactions of p fermions each. So we have this type of Hamiltonian here, where there's some coupling coefficient that you have to choose, or that you typically choose random. But I don't want to go into any of that here. One thing that I want to mention here is that this model as a whole is conjectured to be dual to 1 + 1 dimensional gravitational model in the bulk, but we don't know precisely what it is. However, there is a tractable limit of SYK that is both analytically solvable and interesting, and it's a so-called double-scaled SYK model, so I'm going to denote this as ds SYK, where we take p to infinity, so the number of fermions interacting in each vertex goes to infinity, and the number of fermions overall is also going to infinity, keeping their ratio p squared over n fixed in this limit, and I'm going to call this lambda. Now, in a series of impressive papers, Berkuz and collaborators computed the same correlation functions as the one that I showed you in JT. So the disk partition function and the boundary two-point function. So let me just show them to you. The details don't matter here. The only thing that I want to show you is how similar their structure is compared to those of JT. So this is the disk partition function in this double-scale SYK model. It's an integral over some auxiliary variable theta. There's some density of states factor that appears here. So it's a complicated special function. It's called this Q-Pochhammer symbol, which is essentially an infinite product. And then there's a Boltzmann factor e to the minus beta times a thing that plays the role of the energy. So here I've denoted this parameter Q. It's e to the minus lambda. And lambda was this parameter that was kept fixed in the double scaling limit. And in particular, I want to show you the boundary two-point function and show you how similar it is to JT. So it's an integral of two of these variables, theta 1 and theta 2. We have twice the same density of states as the disk partition function on the previous slide. We again have Boltzmann / Hamiltonian propagation factors. And then we have a complicated thing that couples the theta 1 and theta 2 integral together. Now, this complicated thing, you can also use a math identity to write this, in this case, as a sum of a product of three things. And each of these things only depend on one label that I want to identify as a representation label again. So this is very similar to the thing we did with the gamma functions in JT gravity. So you can write down this kind of formula. Again, there's special functions appearing here, but you can ignore what they are. The main thing that I want to show here is the very similar structure of the amplitudes as in JT gravity. So the main thing that I want to do here is explain, in part at least, explicitly why this is so. And I want to focus on these functions in blue here. And I want to show you that these functions in blue are also representation matrices of a suitable group, or quantum group, as it will turn out, just like the Bessel-K functions in JT were representation matrices of SL2R. So let's play the same game. We first identify the algebra. So the algebra in this case is not an ordinary Lie algebra, it's a quantum algebra. It's a Q deformation of SL2R defined by these relations. So we have the same three generators, H, E, and F, but the right-hand side of this third commutation relation is different. It's nonlinear, and it's parameterized by that parameter Q, which was the same one we had on the previous slide. It's e to the minus lambda, where lambda was a double scaling parameter of the model. And then we need to exponentiate in some way to go to the quantum group. And I want to use the same Gauss-Euler type coordinates. And there is a decomposition known, which was written down by Fronsdal and Galindo in the early 90s, where you write a quantum group element as a product of three exponentials, but the first and third exponential are not ordinary exponentials. They're so-called Q exponentials, which have a modified definition as a series expansion. And also, the gamma, phi, and beta coordinates, they're not commutative in this case, unlike just ordinary SL2R, and they satisfy this non-commutativity relation. So phi and gamma don't commute, phi and beta don't commute, but the other two do commute. So the statement here is that if you're given a representation of the quantum algebra E, F, and H, so you're given three matrices, go through this procedure, you construct some object G, and that object G is then a representation of the associated quantum group. So that's the mathematical statement that's here. And now we can play exactly the same game. We define the left or right regular representation by solving that equation for Li hat. Now these Li hats will not be differential operators anymore. Now they will be difference operators, but you can do exactly the same thing as we did for JT gravity. So they look rather complicated, and again, the details don't matter here. I just want to show you can do this calculation, and there's some sort of difference operators instead of differential operators. So I've introduced the Q derivative here, and there's also appearances of a shift operator and a rescaling operator in these expressions. From these expressions, you can write down the Casimir operator of this quantum algebra, which generically looks like that. You just plug in all of the formulas, and you find this, well, let's say second-order difference operator, just like you had for the SL2R case. And then you just need to diagonalize this thing, just like we did for SL2R, and find that one of its solutions are precisely these functions that I colored in blue on the last slide, these things that we want to identify as representation matrices, and indeed you can do that. If you impose the same type of boundary constraints as in JT, so in that case these were these holographic boundary conditions, you can show that this operator has eigenfunctions that precisely matches with the ones that I showed you well, a couple of slides ago. Okay, so this was the second model. So now let's finally go to the third model, again defined in a completely different way a priori, and this is Liouville gravity. So this is the non-critical string you get from coupling 2D conformal matters to 2D gravity, or the critical string just by taking 2D Liouville CFT, matter CFT, and the ghost CFT with total central charge 0. So let me be a little bit more explicit. So the total action is the sum of the three pieces that we have here. And I just want to show you the Liouville action. So this is the standard way of writing the Liouville action in terms of the Liouville field phi here. And the only thing that I want to mention here is that it has an exponential potential, as usual. And there's a parameter b in that exponential potential. That is, well, the definition of the Liouville CFT. And that parameter b will appear in the next slide as well. Well, and there's some typical notation you could do for, well, here for Liouville CFT, but I won't have need for any of that. I will not have to specify the matter, 2D matter CFT at all. It's just some arbitrary CFT with central charge less than 1, and then we have the usual BC ghost theory of central charge minus 26. Now, without going into the details again, the amplitudes, so again, the disk partition function and the boundary two-point function, they have been determined, so we determined them a couple of years ago, heavily using all the results in Liouville CFT of the Zamolodchikovs. And I just show you the results, and again show you the resemblance with both double scale SYK and the JT amplitude. So the disk partition function is given by an integral over an auxiliary variable S. There's a density of states, which is the product of two hyperbolic sine functions, and then the Boltzmann factor again, e to the minus beta times something that plays the role of the energy. And then the boundary two-point function. In this case, you insert boundary vertex operators in the string theory language. Again, the details don't matter, but you can do that calculation again, and you find a double integral over two of these auxiliary variables, S1 and S2, 2 times the same density of states as you had at the disk partition function, these Hamiltonian propagation factors, and then a complicated thing that couples the S1 and S2 integrals together, playing the same roles as the gamma functions or these Q-Pochhammer symbols for double scale SYK. And this SB is, again, a special function. It's called a double sine function. What it is, it doesn't matter, but it again satisfies a mathematical identity that is very similar to the ones we had before. You can write that thing, so that product of these double sine function, as an integral over some variable x, and then a product of three objects that each depend on just one of these labels that I want to identify again as representation labels. And I again colored in blue the things that play the same role as the Bessel K function did for JT gravity. So I've written it very explicitly here. It's a complicated looking expression. Again, the details don't matter. This is just to show you that one can really do this. Now I want to explain this explicitly again. So are these blue functions representation matrices? Of course, the answer is yes. And we have to identify the correct algebraic structure underlying this. And in this case, it's based, again, on a Q deformation of SL2R. it's related to UQ-SL2R directly, but it takes two copies of this. It's called the modular double, as has been studied and defined by Teschner in many papers. And at the algebra level, the quantum algebra consists of two commuting copies of the ordinary UQ-SL2R algebra. So we have these types of relation twice. So we have 6 generators a priori. And one of them has Q equal to e to the pi I b squared, where that b is the parameter appeared in the Liouville CFT. And the other one has Q tilde, where you replace b to 1 over b. So this is the b to 1 over b symmetry, for instance, is a very famous symmetry in the Liouville CFT. Here it's implemented at the quantum algebra level. And again, we need to think on how we go from the algebra level to the group level, so to the quantum group level. And here we can propose a modified version of this exponentiation. So it's related to the one we had earlier with these Q exponentials. But in this case, we use another Q deformation of the exponential function. It's the so-called Fadeev non-compact quantum dilogarithm. So you can check that this is the correct thing to do. And again, you can compute the Casimir from this. And you can indeed show that if you go through the technical calculations, that this function in blue here is indeed an eigenfunction of the associated Casimir eigenvalue problem. So we have identified the same mathematical structure underlying all 3 of these models, in spite of the fact that they were defined in very different ways a priori. So the main question here is then, why are these models so similar in their structure? Well, you can argue for all 3 of these models for a bulk description in terms of a topological field theory, a so-called Poisson sigma model, which is a nonlinear generalization of the BF model. It has a nonlinear symmetry algebra. And then these can then be written in turn as dilaton gravity models, but with a modified dilaton potential. So JT gravity had a linear dilaton potential. You can argue that the double scale SYK model would correspond to a sine dilaton potential, and the Liouville gravity would correspond to a hyperbolic sine dilaton potential. So all 3 of them seem to secretly be dilaton gravity models. Now, for these 2 other cases, this would then lead to unconventional models of holography that require further study, in my opinion, that would not be asymptotically ADS. So the hyperbolic sine dilaton gravity model is very peculiar. It has, at the classical level, a curvature singularity at what you would have identified as the holographic boundary. And the sine dilaton gravity model, relevant for SYK, it can lead to positively curved regions in the interior of the spacetime, at least suggesting a way to implement something related to de Sitter physics within the UV complete model of SYK, or double scale SYK. So let me summarize and conclude. So I've discussed 3 gravitational models that turn out to share a lot of algebraic structure in their amplitudes. In particular, the amplitudes in JT gravity are governed by representation theory related to SL2R. Physically, well, I studied these 2-sided gravitational wave functions, these Bessel K functions, which are Hamiltonian eigenstates of the 2-boundary Hamiltonian. And mathematically, they are representation matrices that solve the Casimir eigenvalue problem. And then the amplitudes in double scale SYK were governed by a Q deformation of this, related to SUQ11. And the amplitudes in Liouville gravity were governed by the modular double quantum group of SLQ2R. And I have, for these 2 cases, defined and constructed the regular representation of these quantum groups and show that the resulting Casimir equation determines the 2-boundary gravitational wave function in these 2 different cases. And in the end, I argued for a unified description in terms of dilaton gravity models for all cases, but then with different dilaton potentials. Okay, thank you.
Good. No, you get to ask Goshi.
Hi, Thomas. Thank you for this beautiful talk, summarizing a lot of very technical results in an understandable manner. I have a somewhat technical question. If you go back to the first version of the model, so you mentioned here the physical role of the matrix element, but there's also the density of states.
Yes.
And in the first state, you mentioned, oh, it's just the Plancherel measure of SL2R. But, you know, I mean, for people who did BF theory, non-compact group long time ago, somehow that fact was missed. The Plancherel measure of SL2R grows linearly with K and not exponentially.
Precisely.
And that's So can you comment on?
Yeah.
And that's a big change because
No,
in some sense there's not enough states, and so can you say a word about why somehow people miss that, and what's the meaning of this exponential growth?
This is a very important question, and we studied this in much detail. So I had a footnote there that it's not really SL2R. So SL2R has a Planck measure k times hyperbolic tangent pi k, which indeed grows linear at large k, whereas we need a hyperbolic sine function which has this very large density of states. So we proposed in a couple of papers a couple of years ago that the algebraic structure should not really be SL2R. It's supposed to, we argue that it should be a semigroup, a positive semigroup, SL plus 2R, where you restrict to positive matrices. And one can show that that thing does have this k sinh to pi k measure. So that would be our proposal for this discrepancy. Yes. Well, the k sinh to pi k was matched. So the disk partition function was calculated not using these SL2R or related representation theory. It was calculated in many different ways. For instance, Stanford and Witten computed it using like a localization argument. So we definitely know that gravity should have the k sinh to pi k measure with the exponentially rising density of states to match with the JT saddle as well, like the mass versus Hawking temperature relation. So it's definitely true that k tanh pi k cannot work. It has nothing to do with black holes. It has far too few states at high energies. So you need a modification of that. And we gave one proposal for that related to a semigroup. That proposal was very heavily influenced by the Q deformations that I mentioned as well. So this work by Teschner, where they looked at Teichmüller, quantizations of Teichmüller space and so on. And in that case, they also had constraints on positivity of objects, like the geodesic length, for instance, of tubes should always be positive and so on. So in that case, there was a natural thing to consider. And they also have a measure in that Q-deformed setting, which is sinh times sinh, is the same measure that I showed you earlier. And that one has a limit that it goes back to the k sinh to pi k measure. So it's very clear that somehow JT gravity is strongly related to this past work of on quantum groups, work by Teschner and collaborators. So that was for us an inspiration to propose this semigroup picture. But this is indeed a very important and confusing point.
Thank you very much for that answer and for the questions. I know there are plenty of more, but you get to ask them over the lunch break. But first, two other important things. We'll be taking a conference picture, which is going to happen here, but we also have the poster ceremony award. Yes, obviously. Thanks. Thank you for reminding me about that. Okay, the floor is all yours, Sumati. You get to hand out the posters.
So this, I think I can use this. Yeah, thank you. So we have a list of jury members. I'm just a representative of this list of jury members. Andres, Mercedes, Sudho, as well as Michael and Jan Willem, who can't be here today. We had a lot of fun judging these posters. I would say not judging them so much as just listening to them and having the posters explained to us. I'm very uncomfortable having to judge. That's just my personality. But I really enjoyed many of them, and they were extremely well presented, very, very interesting work that was presented. We had to, of course, make a decision, and our decisions were based on three main criteria. It was clarity, clarity of the work and how it was presented, as well as the didactics, how it was explained to us, and its appearance, just how snazzy you made it, and that's the nature of poster sessions, you have to make it snazzy. But we also had extra bonus points for particularly snazzy ones. So I think that given the amount of work that went into making these posters, the amount of effort that each of the poster presenters put in, and the richness of physics that we saw, I would first, before thinking about prizes, want to give them all a really good round of applause. So. And now, roll out the drums. I'm not going to go backward, I'm going to go from the top. The first prize goes to B2, which is Bart Zonneveld. For his poster on recursion for hyperbolic surfaces with defects using tightness. And there was tightness of trousers mentioned here, so that was... so the next prize goes to B17, Eduardo De Angelo, functional renormalization in algebraic QFT. And finally, David O'Connell, non-Hausdorff geometries and their applications. So I want to congratulate all three, but I also want to congratulate many of you who were on our last list. We had to make these decisions, hard as they may be. I wish I could give out prizes to everyone, maybe even an ice cream. That would be very nice, but let's give a final round of applause for the winners.
Thank you very much, Timothy. Okay, I'm going to hand over the microphone to the key organizer.
So at this point, it's my great pleasure to call two people on stage that you rarely see in quantum gravity conferences. However, they played an essential role. So without them, this conference wouldn't have happened for two reasons. A, you wouldn't be here because they handled all the correspondence and the organizers would have gone mad. So it's a great pleasure to welcome Gerti and Adi here. So please take the stage, say hello. Excellent work.
Thank you.
Thank you a lot. And if you take the microphone, I'm able to also hand over. This one goes to you.
Thank you very much.
So really, thank you for all the work you put into this. Okay. And then we are at the last point separating us from lunch, the conference photo. So our conference photographer has already taken the stage. Yes, we should move into the middle. So you have exercised this the entire week now.
Yeah, in case you need to yell at people too.
Yeah. And all people upstairs, please. Ga je misschien op de stoel staan? Zou dat ook helpen? Oké. Nou, er komen er een paar bij. Ja, Beatrice.